Fine. Nitin, if you'd like to take over.
Okay, sure. Yeah, so hello everyone, and welcome to this session of solar atmosphere. My name is Nitin, and I am an assistant professor at IIT Delhi, and I'll be chairing this session today. So this session actually includes five talks and five presentations that will be then followed by a summary discussion session, and where you can ask some additional questions as well. So today in this session, we have a very exciting lineup of speakers, which will be covering a wide range of topics like coronal hole boundaries, solar wind origins, going to like phase simulations and filament morphology. So each total duration is 12 minutes. So each speaker is allotted 10 minutes for the presentation and then 2 minutes for question and answer. So, and I also request all the participants to please use chat box for your comments as well as for questions. And kindly mention name of the speaker for whom the questions is addressed to. That will be very helpful later. Okay, so moving on with the first presentation. So our first speaker is Eduardo Flandes from University of Santiago in Chile. So today he'll be speaking on detection of rapid coronal hole boundary reconfiguration using correlation dimension mapping. So Eduardo, you will have 10 minutes for your presentation, and I will give you 1 minute warning before your time is up for the presentation, and then we'll have question answer. So over to you, please.
Okay. Uh, uh, Good night or good morning in your case. So my name is Eduardo Flandes. I'm from Chile in South America. So today I will present our work entitled Detection of Rapid Coronal Hole Boundary Reconfiguration using Correlation Dimension Mapping. This was my PhD thesis, one of the chapter of my PhD thesis. So the main idea is try to understand how the coronal hole boundary irregularities can give us a proxy about the interchain reconnection process. So for this purpose, I am show you this coronal hole, okay, in this time of period. The open, sorry, the white lines are the PFS, the potential field source surface model, and then you can identify different structure in the this coronal hole. So coronal holes are a region of open magnetic field lines, uh, and they are the source of high speed solar wind streams. The boundary are highly dynamic and continuously evolving due to the magnetic interaction with the surrounding plasma. So the idea is try to quantify the level of irregularity. So the scientific question is, can rapid magnetic recognition events be quantitatively detected through change in the complexity of coronal hole boundary as measured by the correction dimension? So the objective is quantify the level of irregularity at the coronal hole boundary by computing the fractal dimension using the correlation integral and thereby identify traction events associated with the magnetic reconnection. So, okay, fractal is a typical mathematical structure you can identify because there are autosimilarity in different structure in different scales. But in the nature, you can identify fractals, for example, the coastline. Okay, so you have some and you obtain a similar structure with the more and more scale. So for this purpose, we try to quantify the irregularity using the fractal dimension. One method is the correlation integral uh, uh, created by Grayson and Prokesha. So in this idea, you have a line, okay, you have a red line and the blue line. So you need to count the number of points inside each cycle, and then you count the number of the point, and you can identify, for example, the blue one is more, there are more points inside of the cycles. The red line, so you can identify has a dimension equal to 1, but the dimension, the fractal dimension for the blue one is major than 1. So when this method, you get one fractal dimension for all the structure, and then Mason and Heurisky change this methodology, and so they count the fractal dimension for each point along of a coronal hole boundary. So the fractal dimension that you can obtain if you plot in the logarithmic scale the number of points inside of each cycle in function of the radius of these different cycles. And then you plot in logarithmic scale, and this slope is the dimension. Okay, so with this idea, we plot this magnetic, this coronal hole boundary, and you can identify different colors. Color indicates more higher value of the fractal dimension, and color near to blue are more lower values. So the idea is that if you get yellow values, you can get more high complexity in this boundary, and you get blue ones or indicates more regular areas. So with this idea, we build a time distant plot. If you get all the boundary between 2 hours of observation, you can put all the boundary, you can cut and straighten and plot one to each boundary along on the time, so you can get this time dependent CDM plot, and so we can identify Treschen events. Treschen event with different criteria. We take 3 events like examples for candidate for reconnection events. So we took these values, and then we return to the original map, and we identify the region of interest corresponding to these selected areas. And so with this, we try to identify in this AIA image what happened. So here you can identify in the green line the correlation dimension value for each step, for each frame. For example, in the right panel, you can identify, and in the beginning, you have a regular boundary, but then you get a irregular boundary with a major value in the colors. So there are more higher dimension value here, and then you get the same irregular, same regular configuration. So you can identify, okay, here where there are happen. So when we analyze the different AIA channels, we can identify outflow. This is the outflow in different wavelengths. So, okay, this can be a event. But for this proposal, we need to identify the magnetic configuration. So for this kind of event, we use HMA magnetogram, and we plot with the potential field source surface, and we find the embedded dipole topology magnetic configuration. So, okay, maybe this configuration and this outflow is showing a jet. So event number 1 is an event for a magnetic reconnection, because they have all the same characteristics. So for the event number 2, we get the same idea, change in the boundary, and then we plot so the same the average for this for each step. So the black line indicate the intensity in the AIA 193 channel, and we can identify there are a correlation between both curves. So then we try to identify in different channels, and then we can identify here, oh, okay, this is a jet. It's very clear, a jet. They have the same structure that we know about the theory. And when we plot the magnetic field lines using this model, we identify again embedded dipole configuration. So this event number 2 corresponds to a coronal jet. And finally, for try to identify these evolution events, we try to identify the event number 3, but this event don't show any signature clear according to the jets. So for this purpose, we say, okay, this is an event that show increases in the correlation dimension, but not don't implies it's not equal to a reconnection magnetic. So this is a framework for try to understand when we method can work and when don't work. So thank you so much for your attention. And this is was my presentation. If you have a comment or question, please.
Okay, thank you, Eduardo, for keeping exactly well in time. So, floor is open for the questions. So, in the audience, if any of you have any question, clarification, any doubt, you can please raise your hand and then you can ask your question. So, Arpit has a question. Arpit, do you want to unmute yourself and ask question so that others can
Yeah,
also?
yeah,
Sure.
yeah. So I was thinking about, I mean, you were showing the boundary evolution, the coronal hole boundary evolution. So is the emergence of new flexes near the coronal hole boundary are governing those evolution, and are these the direct or indirect signature of interchange reconnection? That's what I wanted to ask.
Yeah, the question is that for one side, you know that the magnetic reconnection, well, the origin of the coronal jets is magnetic reconnection. So when we analyze the change in the boundary, it's a geometric signature. So we are thinking, okay, if I see a geometric signature can identify a magnetic reconnection signature, and with this three example, we say, okay, in 176% we can identify, but it's only one like a proxy. No, no 100% of the events correspond to magnetic reconnection. You know, maybe there are noise or another problems.
Okay, thank you, Eduardo.
Thanks.
You can see one
Thank you.
hand raised. Soumya, do you have a question?
Yeah, so I just wanted to ask that. So you show three cases. In two of those, that you see a clear signature, even in the observation that you see signatures of reconnection, and in one case you don't. You just mentioned that that might be attributed to noise or some other um, specific reasons why you see that. So my first question was going to be why, if there can be any physical reasons you think that it shows up in your matrix in CDM, but you don't see a corresponding reconnection event. And the second part of the question was, if you extend this in further, let's say you set it up as an automated thing running over whole data, how do you have any plans to mitigate this? Like, how do you see yourself solving this? Like, it shows up in your matrix, but there is actually no reconnection event,
Yeah.
rather than
So
manually intervening.
yeah, was the first approach for this event because the physical idea that is that when we have a interchange reconnection, we have a new change in the topology because open magnetic field lines uh, now are closed magnetic field line, and the closed magnetic field line are now open magnetic field line. So there are output of plasma. So this output of plasma uh, can pressure the different structure in the boundary, and this is the reason why my boundary is changing. Okay, so this was a first approach. So the idea now is try to identify different coronal hole boundary in different times and get a more statistical process. So you can put different coronal hole boundary and run this program, identify different regions, and so when this we can identify, okay, for all the candidates we have, for example, I don't know, 50% that even correspond to magnetic reconnection. So it's a proposal, but is the future work is about this one. Yeah.
Okay, yeah, thank you, Eduardo. I can see one more hand raised. Please, Priyansh, make it quick.
Yeah,
Okay.
good question. Nice talk, Eduardo. I quickly wanted to ask, given the three plots that you have made, it's not quite clear. The fractal complexity that you are observing at the boundaries, is it right at the event itself, or is it before the event or after the event?
Okay. Fractal dimension is about analysis for 2 hours. Okay.
Okay.
For each point, for each pixel, for the coronal hole boundary, we calculate the fractal dimension. Each color indicates the fractal dimension. Each color here. So we have a 2 hour of observation. So when you identify this one, you can find, for example, increases in the brightness curve in the black, and then we find the increases in the grid line. So this is fractal curve. Green and black is the intensity. So this we can see that there is sensibility for this method to the physics process.
I see. Okay, thank you.
Okay.
Yeah, but actually we are running like late for this talk. I also have a few questions, but I will probably save them for the discussion session. So thank you, Eduardo, for the nice presentation.
Okay,
So
thank you so
we can,
much.
yeah, thank you. So now we can move to the next talk of the session, and that is by Vishwajit Mondal. So maybe you can share your screen. So Vishwajit is a NASA postdoctoral fellow at Marshall Space Flight Center, and his talk is titled "Slitless Spectroscopy: From Second Flight of the Marshall Grazing Incidence X-ray Spectrometer." So Vishwajit, you have 10 minutes for presentation. I will give you 1 minute warning before your time is up. So over to you.
Thanks. Hello, everyone. My name is Bishwajit Mondal, and I am a research scientist at University of Alabama in Huntsville. Earlier, I was a NASA postdoc at NASA Marshall. So recently, it is changed. So today, I'll talk about slitless spectroscopy. So this is in the background, you can see how the slitless spectroscopic image of the sun looks like, that is taken with second flight of Marshall grazing incidence X-ray spectrometer. So here, this repeating pattern, you can see they are basically coming from different ionization states of different element emitting from the sun. So here is entire Magix2 team who are basically involved in this project. So Amy Weinberger is PI from NASA Marshall and all others. So let's start with why do we need coronal UV or X-ray spectroscopy? So this image is showing the image from STO AIA. You can see that how dynamic the sun is as a function of time as well as space. Now, to probe this plasma condition, we need to know what is the temperature, density, elemental abundances, velocity, and equilibrium conditions. Now, all these things we can get from UV and X-ray spectroscopy. So that's why they are important. So let's start with what are the other methods that we usually use for spectroscopy. So one of the method we use widely used is broadband X-ray or UV spectroscopy. So this kind of instruments are flown multiple times, and like one of them are with Chandrayaan-2 orbiter, which is XSM, Solar X-ray monitor. Another operating instrument is SOLEX on board ITL-1. So this type of instrument, they observe solar X-rays and give us the spectrum with a sun as a star mode. That means there are no spatial resolution. So in this case, once we get the observed spectra, if we model it, we can get temperature, elemental abundances as a function of time. But there is a huge drawback, there are no spatial resolution. On the other hand, if we use a slit-based, sorry, hello.
Please carry on, Vishwajit.
Okay, I'm sorry. So on the other hand, like slit-based spectroscopy, where we can get the spectrum along the slit, wherever the slit is located on the sun. So in this case, we can get spatial information, but there is a drawback. So to cover the entire active region, we need to raster, we need to place the slit for multiple location, and that rastering process takes like few minutes to a couple of hours for an entire active region. So this is a disadvantage for like a dynamic event like solar flares, where the flaring plasma is very dynamic as in very small time scale of fraction of second or couple of seconds. So you'll miss information through this kind of spectrometer. So all these, problems can be solved with slitless spectroscopy, where we can get the spectrum without a slit or without a slit basically. So this is one example where you can see the repeating image of the sun. So these repeating patterns are basically associated with different wavelength. So this is one example of slitless spectroscopy from early 1970s. So this was the first kind of slitless spectrogram flown by NASA on board Skylab. So astronaut takes this kind of images of the sun in 1970s, but at that time we have limited computational capability. So interpreting this kind of data was very challenging. So you can see that how this sun here that is overlapped with next sun, they are associated with different wavelength. Now interpreting or disentangle this kind of data was very challenging. So in last decade at NASA Marshall, so are basically developing specific kind of this kind of technological advanced instrument for slitless spectrometer, where we can disentangle this information from this kind of data. And one of the instrument is Marshall gauging incidence X-ray spectrometer. So these are sounding rocket instrument, and this is a layout of the instrument. We have X-ray optics, grating assembly, where basically disperse the incident X-rays, and then a detector at the end. So this is how the whole MAGIC's telescope looks like. So this is in our calibration setup at NASA Marshall, where this is a vacuum chamber. This is a beam line. So instrument is attached with the beam line. So it was launched on July 16, 2024. So through sounding rocket campaign. And as it was a sounding rocket, we get only one chance to observe the sun. So before launching, we had to do like lot of forward modeling and calculation where to observe, where to point our instrument, because once it go up, we only get like 5 minutes or so to target our observation. So these are one set of simulation just before the launch. So we decided we will launch and we'll point our instrument in this along this axis, so that we can capture all these three active region on the sun, and we should get an image like this. And this was our real-time flight observation. And it was amazing to see that whatever we were predicted just before the launch, we capture all of this active region during flight. So this is the overview of MAGIC's 2 observations. We observe these three active region on the sun. So this was the extended active region that was our primary target. So you can see the repeated pattern of the same region, and the primary emission lines are marked at the top. So basically here x-axis is the wavelength and y-axis is the spatial location along the y-axis here. Now interpreting this data is challenging because there are spectral and spatial overlap. So MAGIC's team developed some inversion technique to disentangle this inversion, but so far this inversion was limited to only get the temperature structure of the sun. And recently we have extended this inversion technique to get abundances as well as temperature and emission measure. So I'll not go into details of this mathematical formalism, But now I will basically show you to apply this method on actual Magix data and what we get in the preliminary analysis. First, let's focus on the primary target, which was at the center of our field of view. So this is AIA image of this extended active region at the center. And this is from our Magix inversion. So here, these 4 panel, so they are basically emission measure map of this region. So where the first panel is at lower temperature, around 1 to 3 million Kelvin, and at the bottom right here, so this is at very high temperature, 8 to 10 million Kelvin. So you can see that this hot temperature is concentrated towards the center of the active region, whereas the cool plasma is present everywhere. And if we see the emission measure curve here, so here y-axis is the emission measure, which is proportional to the density square, and x-axis is the temperature. So region 1 and 2, which are basically high temperature portion, our emission measure is very, very less. Whereas if you go to the region 3, there is extended high temperature emission. Similarly, these are spectrally pure map where we can get magnesium 12, iron 19, as well as these are basically hot emission, as well as we can get cool structure of oxygen 8 or so. Also, as we have like multiple ions of the same element, we can, from the ratio of them, we can infer what kind of heating frequency or heating is happening on the in the plasma environment. So this is one example where we basically saw the ratio of ion 17 by ion 18. Here at the core, you can see the ratio is high, which indicate the frequency is low. At the periphery, the ratio is low, so that means there is a high frequency heating. And this pattern is correlated with the simulation result, where we showed that at the core there is low frequency heating are dominated. At the periphery, high frequency heatings are dominated. So this is another target, which is another active region. So this is another interesting region where towards the end of our flight, we capture a hot flaring loop on the at this region. So this is again from the Magix inversion, we can get the emission measure map, and you can see at towards the end when this flaring loop appear, how this high temperature is enhanced in the flight data. And this is how the abundance varies as a function of time and space for this particular region. So on the left side, this is AIA image. You can see extended loop structure above limb. And this is inverted from Magix. And the right-hand plot basically shows the abundance map. So you can see that at the lower height of this loop structure, the abundance are low. At upper height, it is always higher. This is something interesting, and to the best of our knowledge, this is something, a new observation in this temperature and energy wavelength regime. So we also have coordinated observation with solar orbiter sticks. This is just a summary, and we also basically compared how this flaring light curve looks in sticks and Magix. So these are coming from Magix, and this is sticks, and this is how the spectrum looks like. So Magix we can give us high resolution spectrum at lower energy, where sticks at higher energy. So that would be something interesting to do joint analysis. We also have joint observation with Aditya L1 Solex. That can cover the intermediate spectrum in between in this region here, basically. So with that, so this is the summary. So I'm leaving it to read out the summary. And so we have a good observation with Magix 2 flight, and this is a very rich data set, and we can do many things with this data set. So feel free to reach out to us for if you are interested in this data set for any studies. So with that, I would also like to mention, like with the success of Magix 2, a third flight of Magix is also scheduled to launch in this year. So we are expecting to get much more to do from this kind of data. So thank you.
Okay, yeah, thank you, Vishwajit. Yeah, so we don't have much time for a question. Maybe one quick question if anybody has, else we can have the question answer in the discussion session, discussion part. Anybody, any quick question? Okay, yeah, if not, yeah, thank you, Vishwajit, once again for this wonderful talk. And
Thank you.
we can now move to the next talk of the session, and that is by Arpit Kumar Srivastava. And Arpit is a postdoc in Southwest Research Institute. And today he'll be talking on understanding solar wind origin in large-scale structures by probing dynamics in a pseudo-streamer. So over to you, Arpit. I'll give you 1 minute warning. Thank you.
Thank you, Nitin. Thank you for the introduction. Am I audible and my screen is visible? Hello.
Yes, yes, please go ahead. We can hear and yeah, see the
Okay.
screen.
Okay. So I would first like to thank the organizers for inviting me to present my work here. Solar wind origin is a multifold, multidimensional problem, and I will be presenting only pieces of this problem in the context of large-scale structure by probing dynamics in a pseudo steamer using inner middle coronal observation of solar orbiter, and we'll see how this observation gives us an idea about the origin of the solar winds. So let's begin with what we can understand about the solar wind origin from the in situ observations. There are Ulysses observed the latitudinal variation of the solar wind speed, and they found that there is during solar minima there is a well distinct separation between high speed winds and low speed winds. So high speed winds are coming from polar regions and low speed winds are situated near the equatorial regions. Based on that, solar wind is broadly characterized into fast and slow solar wind. And in the solar maximum, as you can see in this right plot, the situation is very complex. You have very intermixed sources of slow and fast solar wind, and that is due to the global magnetic topology during solar and minimum and maximum as well. So if you look at the solar wind emanating from the open field lines through the heliosphere, they should have low iron to oxygen ratios because they are coming straight off the photosphere, and in the photosphere you have this kind of value, and fast solar wind kind of follow this. If you can look at these regions in the red, which are associated with fast solar wind. So, but if you look at the slow solar wind can have similar ratios, but sometimes at some intervals, you will see that there are high iron to oxygen ratios, which is generally found in closed field regions in the solar corona. So the question is how slow solar wind is emerging from closed field regions. And the primary candidates which people have been seen in the literature, that there are large scale structure, and this is one of the schematic diagram of the large scale structure such as pseudo streamer and helmet streamers. These structures are characterized by open and closed boundary. You can see here there are open and closed field lines within these structures, and these open and closed boundary are susceptible to the interactions. And this is one of the animation by Viper et al., where they have shown that how open and closed field lines are interacting. And during the interaction, you see that uh, just something. Yeah, during the interaction, you see that you have reconfiguration happening where the plasma from closed field lines generally is escaped in the heliosphere during interchange reconnection. And you will also see the outflow and outflow signature. So uh, the problem is this kind of interaction has been indirectly seen in different type of observation, and has been seen in the theoretical and simulation studies, but in the observation there is no direct evidence of interchange connection due to lack of observation covering dynamics within these structures. Also, if you look at the height location at which these are happening around 1.2 to 1.3 solar radii in a pseudo but there could be contribution from the base, which is the outflows or downflows, which are coming from the base, which can contribute to the magnetic topology of pseudo streamer and solar wind in those structures. So, if you look at the observation near the base of the solar corona, you will see that there are small scale reconnection at the base of the solar corona, which can produce waves and flows. But what happens in the large scale structures? Do we see such kind of things? We don't know. So, what kind of dynamics we see near the base of large scale structure, which can contribute to solar wind, is one of the question we are trying to understand. So, our motivation is pretty clear. We want to understand where and how the solar wind emerge from the large scale solar structure, pseudo shimmer in this case, and do we see dynamics near the base, like waves and outflows? What are their properties? Can we detect evidence of interchange reconnection in pseudo streamers? And if yes, what kind of composition we obtain in large scale structure near the base or I mean near the base in the low corona? So with that motivation in mind, if you want to ask those questions, if you want to investigate these kind of questions, you need observations which have which have instrument observing the different regions in the solar corona, such as inner and middle corona regions, and that's where the solar orbiter comes in picture. So solar orbiter has different instrument covering different regions. So we have an observation of pseudo streamer above the limb, which was observed by full sun imager on the solar orbiter, and you can see a nice pseudo streamer sitting on the limb, and the foot points of these pseudo streamer were observed by two different instruments on the solar orbiter, HRI UV, which is high resolution imager going up to 100-kilometer scales, not achieved it by any of the instrument earlier, and you have spectroscopic observation from SPICE. Here I am showing the raster image from one of the lines from the SPICE. So combining this different field of view observation, we can ultimately get an overall picture of how the solar wind is emerging from these large scale structures. So we first look at the base of the these structures, and this is one of the animation of the one of the foot points, and you see there are outward propagating features near the base, and these are going into different stands. So if you make a time dimension plot along this fine scale structure, along this dashed red line, you will see that there are outward propagating features represented as slanted ridges in the XT maps or the time distance maps. And these slanted features or upward propagating features are called propagating disturbances, PDs, and these have a speed of 121 kilometers per second. If you want to put this into context of the middle corona, people have found earlier in the middle corona using CV observation that there are fast outflows around in the speeds of 50 to 150 kilometers per second. And those fast outflows actually, I believe, can be connected to these PDs, but we don't have studies yet. So we are looking for those studies. And I mean, these PDs are repeating at fixed intervals. So we looked at the periodicities of these PDs and we found that they are periodic in nature. And so these kind of these properties gives us an idea what kind of dynamics is happening at the base. And ultimately, this PD can supplies mass flux to the solar wind coming from pseudo-streamer, because pseudo-streamer has been studied in the in situ a lot, and this kind of study kind of gives a perspective what could be the origin happening near the base and inside the pseudo-streamer. So we also studied the base using SPICE observation, and we found that there are blue shift in the SPICE observations and near the base. And these blue shift, if you plot the contour of blue shift on the structure itself, those are at the same location where we found PDs. But the problem is these are the limb structures, and we cannot say with assurance that these blue shifts are downflows or upflows, and that's why we can do PFSS on and we are currently doing some 3D reconstruction to understand the geometry of the pseudo streamer and the corresponding downflow and outflow signatures, interpreting those signatures. What even if we understand there are previous observation from eyes which have showed that there are downflows near activation edges, and if they correspond to downflows, we interchange reconnection seen which is supported in FSI observation, which I will show in the next slide, will explain these downflows as well. So SPICE observation also provides to some extent about these solar wind origin in these large scale structures. But in the middle corona, using FSI observation, we saw that there are interaction happening near open close boundaries. These blue arrow shows the downflows, while the green arrow shows the interaction region. So there are interactions happening near the cusp. After that interaction, you see some downflows. But why we are calling that those are interactions? How we can call that those are interactions? We can call that only when we see that. And that's what we have shown here, where you take a slit perpendicular to the interaction measure, and you see that the structures inside the pseudostemer core are coming towards the or you can say that the structure near the boundaries, the open field lines near the boundaries, and the structures inside the pseudostemer are coming close to each other. So that's why I'm saying that there is interaction happening between open and closed field line, between in near the open and closed boundary. And what we get from these interactions, we get, if you take a curved slit along those downflowing plasma which I showed earlier, you will see that there is downflow existing, and these downflow are coming after the interaction between those open field lines, those open and closed boundary I've shown earlier in the previous slides.
That is
And that's why I'm
helpful.
saying the okay. Okay. These downflow provide evidence of interchange reconnection occurring near the open coast boundary, but only problem is that we should have simultaneous outflows, but there are several factors due to which we didn't see any outflows simultaneous to these downflows, and maybe future studies can also reveal such kind of things with different instruments like PROVA 3 and more FSI observations. Now, we also looked at the abundances near open coast boundary using SPICE. SPICE can only go up to maybe 100 megameter of the solar limb, but near the base you see that so the value of 1 correspond to coronal abundances, coronal composition, and the value of 0 correspond to photospheric composition. If you see the region of interest R1, R2, R3, R4, you will see that the elemental abundance near the boundary have the coronal composition, and open closed boundary has been invoked as the primary regions where interchange reconnection can happen, and in situ observation have already shown that solar wind has coronal composition. That's why we are saying that these boundaries could be possible source of flow solar wind. So in summary, we looked at the inner corona, we looked at the middle corona, we looked with imaging observation, we looked at with sonic observation, and we studied uh, what could be the scenarios happening in these large structures which are giving rise to physiological performance in general. So that's all from my side. Thank you for listening to me. I'm open for any questions.
Okay, thank you, Arpit. So the floor is open for the questions. So from the audience, if you have any comment, any questions, you can raise your hand. Okay, if not me, maybe I can ask one question, Arpit. So this 11-minute periodicity that you found in PDs,
Yes.
right? So this is very
Yeah.
interesting, but what do you think it is like driven by? Is it like the photospheric oscillations or like some reconnection process itself or something like which is intrinsic to the coronal structure like the pseudostreamers that you have?
No, so PDs are kind of ubiquitous in several structure in the solar corona. The thing how they are originating, I would just want to give a spoiler that there is no consensus in the community regarding their origin. It's highly debatable right now, but there are a few possible scenarios, like there are quasi periodic high speed upflows which can generate these PDs. In terms of, if you understand them as waves, because PDs, we don't know whether PDs are waves or flows. So if you understand, if you consider them as waves, there could be, like you said, the photospheric P mode, and depending on the what is the geometry of magnetic field line at those locations, these P mode can be leaked, and they can appear as slow waves in these structures. But there are some evidences of spicules related to these PDs in the polar region. So there are multiple scenarios which can give this, and every scenario is no I mean, you cannot uniquely explain whether these are these PDs are waves and flow, and that's the problem. So origin has multiple scenarios. That's what I can say.
Okay, okay. And in literature also, is it mostly around 10, 11 minutes, or are there other periodicities also which are?
So that's a good question actually. So in the solar corona, we see in these PDs in the range of 3 to 30 minutes actually. In the polar region, you will see larger periodicities as well. In the sunspot, you see 3 minutes periodicities as well. In different regions, we see different periodicities as well. So it's not very unique that you will see only 11-minute periodicities. There is one recent study by Vincenzo Andretta using METIS, who shown that in the outer corona, actually in the middle and outer corona, there are some periodicities in the outflows, and those periodicities were associated with these PDs. But the connection between inner and middle corona has not been established yet. So that's what we are looking at right now with some PhD students.
Okay, yeah. Thank you very much, Arpit. Yeah. So now we can move to the next talk. So our next talk is by Itzayana, and she is from Yunnan, Mexico. And her talk is titled 3D MHD Numerical Simulations of Solar Flares. And she is investigating the role of different dissipative terms in this. So over to you, Itzayana. So I'll give you 1 minute warning. Thank you.
Okay. Hi, everyone. My name is Itzayana. Thanks for the introduction. It's a pleasure to be here. And today, I'm going to talk about our work on numerical simulation of solar flares. In particular, I focus on the different dissipative, different physical processes that affect the thermodynamic evolution and formation of post-solar flares. This work was developed at the NES of UNAM in Mexico in collaboration with the Dr. Jose Juan González Avilés. And so to start, let me briefly introduce physical context. First, the solar flares are an explosive event in which a huge amount of magnetic energy is converted into kinetic and thermal energy, driven by the magnetic reconnection process. The results are plasma heating and the development of the post-flare loop arcades. While magnetic reconnection governs the global dynamics, an important question arises, and is how do dissipative terms affect this process? In particular, we want to understand their impact on the thermodynamic evolution of post-flare loops. And for that, we resolve the 3D resistive MHD equation systems that includes the mass, momentum, and energy conservation, and describes the magnetic field evolution through the induction equation. The system of equations you can see at the right-hand side of the slide, and we focus on the energy conservation because it's here where we introduce the dissipative processes like resistivity, thermal conductivity, coronal heating, and optically thin radiative cooling. The way for solve this system of equations is numerically was using the Pluto code. It is a open access code, and the numerical equation are implemented in that. So all simulations are performed using standard numerical methods like finite volume scheme with a second-order Runge-Kutta integrator and a mid-mode limiter for the linear reconstruction. We use HLLD Riemann solvers and use fixed boundary conditions at lower boundary and open elsewhere. All simulation use a 3D Cartesian domain, extends from -10 to 10 megameters in X and up to 20 megameters in Y and Z directions. Use 400 by 400 by 50 grid points with an initial magnetic field approximately of 30 Gauss. This initial configuration looks like in this picture. So with the numerical setup in mind, we can move to the diagnostics and analysis. We study 4 main cases listed here. The case level by 2 is included only resistivity. The case number 6 is with resistivity, constant coronal heating, and optically thin radiative cooling. The case 7 is the same as the case 6, but this time we use a height-dependent coronal heating. And finally, in case 8, is the same like in case 6, but this time we introduce the thermal conduction. And with this established, we study the energy evolution, the thermodynamic structure, and we compute synthetic emission maps in 2 different channels. Okay, let's move to the results, starting with the energy evolution. As you can see in the figure, at the early times, all cases shows similar behavior where the magnetic energy is converted into thermal and kinetic energy, and at later times, the solutions diverge. This is due because optically thin radiative cooling reduces the thermal energy. The reduce is from the 13% to 9% at the final of the time evolution. For other hand, or in addition, in the energy conversion, the form that we use for the coronal heating is not affect the evolution. So this highlights the importance of including these two processes in the energy balance. The next thing that we studied was the effect of thermal conduction. Here we present 2 cases, the case 2 without thermal conduction and the case 8 with thermal conduction. On the left, without thermal conduction, heating is highly confined and this producing a higher peak temperatures. And on the right, when thermal conduction is included, the energy is redistributed along the magnetic field lines. So this results in a smoother temperature structure and a lower peak temperatures to approximately 2 orders of magnitude lower than for the case 6. And finally, we compute synthetic emission maps for the case number 8, where the dissipative process are included. These maps correspond to the 15th seconds of evolution. And as you can see at the pictures, we have bright emission at the loop top, which indicates the presence of the plasma heating. And we also observe this cusp-shaped structure, which is an typical signature of magnetic reconnections, and the morphology is consistent with the model of magnetic reconnection.
1 minute is.
Yes. Finally, a stronger emission in the AIA 131 Armstrong channel indicates the presence of hotter plasma. So to summarize, we can detect that the magnetic reconnection governs post-flare loops dynamics. However, dissipative processes regulate plasma thermodynamics. For other hand, optically thin radiative cooling prevent excessive heat accumulations, while thermal conduction redistributes energy along magnetic field lines. The simulation reproduces key morphological feature observed in the AIA data. Thank you for your attention.
Okay. Thank you very much, Itzayana, for the nice presentation. So floor is open for the questions. So just raise your hand if you have any comments or questions. Okay, Soumya, yeah, do you have a question? If yes, please unmute yourself and ask your question.
Yeah. So thank you for the very nice talk. When you talk about the kinetic energy, what kind of kinetic energy are you talking about? Do you have like CMEs erupting in your simulations, or just the material within Corona, the kinetic energy they have like within the flare arcades because of the reconnection and eruption?
I refer to the increase of temperature of particles of the plasma.
Okay. Okay. Thank you.
Yes.
Yeah, thank you. Pratik, do you also have a question?
Yes, yeah, thank you. Very, very nice talk, and happy to see such a use case of Flutocode. So I was just wondering, you are using HLLD and as well as thermal conduction is also enabled. So what are you using for divergence cleaning? Is it air to waves or hyperbolic divergence cleaning or constraint transport? What are you using?
We use a divergence force.
Hyperbolic divergence. Okay, got it. Okay. So do you see any checkerboard artifacts, any instability anywhere in the simulation domain?
I can understand you.
Means, do you see any artifacts because of hyperbolic divergence scheme anywhere where reconnection is happening or anywhere in the simulation domain?
Sorry,
Okay, maybe I will write in the
cannot
chat.
with the
Yeah.
English. I understand you. If you
Yeah.
want to write in the chat.
Yes, yes, I will write in the chat. Thank you.
If you can write it in the chat, Pratik, and I can ask
Yeah.
a question in the meantime. So, Itzayana, can you tell your simulations how sensitive they are to numerical resolution, numerical solvers that you're using, and like the grid effects?
Okay. The resolution is important because when we increase this, we can appreciate new structures, but this not affect the evolution of the general solar flare.
Okay, yeah, thank you. So are there any other questions from the audience? Okay, if not, yeah, thank you once again, Sayana, for the nice talk.
Thank
And
you.
we now move to the last talk of the session, that is by Jane Jacob. So he's working at Indian Institute of Astrophysics, and he will be talking today on the morphology of solar filaments, chirality, bow orientation, skewness, and eruptive behavior. So I hand over to Jane. Yeah, please share your screen, and I will give you 1
Am I
minute.
audible? Am I audible?
Yes,
Yes,
you
yes.
are audible. You can share your screen and start with your presentation. Over to you.
Can see my presentation, right? Can you see my presentation?
Yes, yes. It's
Okay.
good.
Hello, everyone. Thank you for the opportunity to present my work on morphology of solar filaments, chirality, bulb orientation, skewness, and eruptive behavior. Myself, Jane Jacob, PT, postdoctoral fellow at the Indian Institute of Astrophysics. This is my overview of the work presentation. Solar prominences are loop-shaped magnetic structures embedded in the solar atmosphere, and it stays against the gravity. And a solar prominence also can be named as filaments when it appears on the disk, and it classifies when it appears as a atmosphere like prominences. It also classifies like a cohesion and active region according to its presence with the active region. It has a lifetime of few hours to couple of days, and it has a temperature ranges from 4000 Kelvin to 20,000 Kelvin. You can see the cohesion prominence here and a active region filament here. The magnetic helicity of active region. Active region forms through the process of magnetic flux emergence, and it is mostly associated with the sunspot. The magnetic helicity is a measure of Newtonness, and it is given by the expression integral A dot P dV, where A is the magnetic vector potential and B is the magnetic field. And for a case of force free magnetic field, it can be written like a del cross B is equal to alpha b, where alpha represents the force free parameter and it gives the proxy for the magnetic helicity. Halley introduced a magnetic helicity, hemispheric helicity rule, which says that a active region has a preference to helicity, that in northern hemisphere it has a preference to negative helicity, and in the southern hemisphere it has a preference to positive helicity. So when we comes to the filaments case, we don't have the more observation on the coronal magnetic field. So we have to find the helicity of the filament. We have to move to study another features like chirality. So the chirality has a representation of helicity of the filament. So this chirality can be estimated using bearing sense of the filament barbs or skewness of the coronal arcade. As in the figure, you can see the barbs orientation, and it can be classified into textile filaments like this orientation of the barbs, and a sinistel with this orientation of the barbs. So there is a one-to-one correspondence with the filament chirality and a magnetic helicity sign. That means it is, if it has a dextral chirality, it has a right bearing sense of the barbs, and it represent a negative helicity sense. If it has a sinistral chirality, it represent the positive helicity, and it will have a left bearing sense in the filament. In when we comes to the skewness of the coronal arcade, the blue lines represent the magnetic field of the coronal arcade, and the dextral chirality case or a negative helicity case, the skewness of the coronal arcade will be left skewed, and in the sinistral or a positive helicity case, it will have a right skewness. The motivation of the work is like as we discussed that there is no observation for the coronal magnetic field for the filament magnetic structure. So we have to detect the magnetic helicity and magnetic structure. We have to use some indirect methods to estimate its magnetic structure or helicity. And we have to find the stable magnetic structure of the filaments, and how the influence of the associated solar features in the filament magnetic structure. Also, we try to estimate the magnetic helicity rule in different types of the filament and the eruptive nature of filament and its helicity relation. For this analysis, we uses observational data from ground-based observatory and a space-based observatory. And the time of observation from December 2013 to January 2014. So we classify the filaments in this analysis into four categories. According to association with the active region, we can classify the filament into three: quiescent, intermediate, and active region. According to chirality of the filament, we can classify it into textile, sinistral, chirality filaments. According to the magnetic structure of the filament, we can classify it into sheared arcade, flux of morphology filaments. Eruptive nature of the filament, it can be eruptive or non-eruptive. So when we comes to the bearing sense of the chromospheric filament, the chirality can be estimated using bearing sense of the chromospheric filament. We found 31 filaments showing bearing sense, and in the northern hemisphere we have seen 14 filaments, and in southern hemisphere we have seen 17 filaments. In the left panel shows the example for the left bearing bar filament with the left bearing bar, and its schematic representation is shown here, and a filament with the right bearing bar is shown in the right panel, and this orientation shows the right bearing schematic diagram. So according to the bearing sense, we can classify it into as PETSO method. We can, if it has a right bearing sense, we can classify it into a textile chirality, and if it has a left bearing sense, it can be classified into a sinistral chirality. So from this bearing sense, we estimated their chirality. Then we found that textile filaments are dominant in the northern hemisphere. Like it has a 79% of filaments have the right bearing sense, and when we comes to the northern hemisphere, 76% of the filament having left bearing sense, and rest of them having right bearing sense. So next classification of the solar filaments is like according to the association with the active regions. So in this study we have quiescent filaments, 10 quiescent filaments, intermediate filaments of 15, and active regions 10. Then according to the chirality estimation with using bearing sense, we checked the how they were obeying the hemispheric helicity rule. So when we checking the quiescent filament case, we found that all the quiescent filaments are following the hemispheric helicity rule. And in the intermediate filament case, 67% of the filaments are following the hemispheric helicity rule. And active region filaments case, 60% of the filaments are following the hemispheric helicity rule. So again, another part is skewness of coronal arcade. So we with the filament we found coronal arcade in 18 filaments, and in the northern hemisphere we found 3 coronal arcade associated with the filaments, and southern hemisphere 15 filaments having coronal arcades. So the coronal arcade having this orientation will be considered as a left skewed, and this orientation with the filament can be considered as a right skewed. So one of the example for the left skewed coronal arcade with the filament in SDO AAA 193 image is shown here. For the right skewed coronal arcade is shown in this right panel. So in this study, we found that all filament in the northern hemisphere having left skewed coronal arcade, and all the filaments in the southern hemisphere having right skewed coronal arcade. When we using this estimation, we have estimated the bearing sense and a skewness of the coronal arcade associated with the filament. Using these two estimation, we can find the magnetic structure of the filament. So the for orientation of the coronal arcade and a filament barb orientation, we can classify the filament into two type of the magnetic structure: flux rope or sheared arcade. So the classification is like this. If the filament having left bearing barb with dextral chirality or right bearing barbs with sinistral chirality, it can be classified into sheared arcade morphology filaments. If the filament having left bearing barbs with sinistral chirality, okay,
One minute.
right bearing barbs with the dextral chirality, it is having flux of morphology. So this is one of the example for the flexure of morphology filament. We found in this filament having left bearing sense and a skewness of right skewed, and this is the schematic for that morphology. So when we comes to the estimation, we found that a magnetic structure, that a sheared arcade having 3 sheared arcade morphology and a 15 filament having flux of morphology. So most of the filaments having flux of morphology, and we found that all the cohesion filament what we found in this study having flux of morphology, and most of the filament having flux of morphology as seen in this pie diagram. So when we other studied the eruptive nature of the filament and a hemispheric helicity rule. So we found eruptive filament case, 6 filaments are following the hemispheric helicity rule and not following 2 filaments. In the non-eruptive case, following ones are 16 and non-following are 6. So when we come to the pie chart, we can see 75% are following. In the case of non-eruptive case, 73% are following. It means that no influence on the hemispheric helicity rule and a eruptive nature of the filament for the hemispheric helicity rule. So these are the conclusions of my study. Like I have tracked 35 filaments and I have studied its hemispheric helicity rule and skewness, and we found no correlation with the eruptive nature and hemispheric helicity rule. Sir, reference. Thank you.
Okay, thank you, Jen. So floor is open for the questions. If there are any questions, please raise your hand. So in the meantime, maybe I can begin. Yeah, so Jen, my question is like during the evolution, like did this chirality remain strictly conserved during the filament evolution with time, or there are also transitional phases where the chirality changes?
Yeah, we have some filaments case, we have seen the chirality changes. Because we can see like some filaments when it evolves, it can change the morphology also. So initial stages it will have a sheared arcade morphology, while reconnection and all it will leads to a flexure of morphology. So that mostly it will give a stable structure. So this we in one or two filaments in this region we have seen its bearing sense change, and the arcade associated with it is not changing. So this from this analysis we can say that its magnetic structure is changing and it is moving to a good stable flexure of morphology type.
Okay, okay, nice. Okay, maybe one more question since like there is time. So, did you also look for any pre-eruptive signatures in filament morphology? Like, are there any changes in the barb structures or skewness before the eruption? Like, did you look at the evolution, like time evolution when there is eruption? Like, is there any like noticeable change in the barb structure or skewness, something like that?
During this time, we didn't. I didn't find any markable change in bearing sense just before the eruption
Okay.
in the skewness.
Mhm. All right, yeah. Thank you, Jane. So since there are no further questions here, so yeah, thank you once again. And thanks to
Thank
all the speakers in this session for the wonderful talks. And yeah, so now we are heading towards the last part of the session, that is summary and discussion. So maybe floor is open. So if any of the audience has any question to the five speakers that we had today, you can just raise your hand and ask questions to the speakers. Okay, just to begin with, maybe, okay, Jane, you can actually unshare your screen now. Okay, so just to begin with, I would like to ask Eduardo that I hope he's here. Okay, so Eduardo, my question is like the method that you described, like the correlation dimension mapping. Can we also extend this method to active regions, like to study the heating of the coronal loops? Because there are increasing theories which suggest that coronal loops are also getting heated up because of the small scale reconnection happening at the photospheric level. So can we apply this changing or the this correlation dimension matching, like increasing irregularity of the boundaries to the sunspots as well, to study the, like, is there can this lead to the coronal loop heating as well?
Nitin, I think Eduardo has left. I think
Okay,
he's the
okay.
only person among the speakers who has left. But I
Oh,
think on the coronal loop, there are many speakers who have talked about the coronal loop, like Arpit and all those. Maybe they can attempt this question.
yeah, sure, sure. Please feel free to attempt. Just share your views. Like, what do you think?
I mean, the thing which Eduardo was showing was looking at the boundary of the coronal hole boundary variation or evolution. So I'm
Yeah.
still thinking how those kind of method could be used for. I mean, in principle, it should be used for small scale transients in the active regions, but coronal loop evolution are not very simple. I mean, not very similar to what whole boundary evolutions are, and that's why there is. I mean, I'm not able to think any a very obvious way to attempt that coronal loop morphology or coronal loop evolution thing with the method I've already used. I think so.
By measuring the
That's
fractal
what my
dimension,
view is.
yeah, I means I don't know, like, because in granules also, like I have also done one
Mm,
work with the students. So for granules also, we
mm,
can check how the fractal dimension is changing. Like, is the granule smoother or it's more irregular? So looking at Eduardo's work, I thought like it is also possible to do for the larger structure, like the sunspot boundary. Like, is it more homogeneous, more regular, or is it more irregular? And if it is irregular, maybe like correlation can be checked. Like, does it lead to like more enhanced heating in the coronal loops or not? Yeah. So that is what I was
yeah.
like thinking in the direction of that. Anybody else like want to share their views? That Prateek has raised his hand here.
Yeah, I
Yeah.
have. I also had the question for Eduardo, but he has left. Maybe I will
Mm,
just make it open. And I was wondering that there has always been a debate whether to use PFSS or nonlinear force free for especially for that kind of work. So, what you guys, solar atmosphere people, think that should we stop using PFSS for local active region study, or is it okay to use that? Matt was also kind of touched upon this topic yesterday while he was explaining the visual mission. He was saying that we should go beyond the line of sight magnetogram and focus on vector magnetogram. So, what do you guys think about that?
Um, hi.
yeah,
Uh,
go ahead.
I think if I mean, from my limited understanding, like if you are looking for large scale structure, even in the active region, maybe PFSS would be helpful. But if you are looking for a small scale structure then PFSS may be not a good approximation.
Yeah, I also share the same views. Like maybe for the large scale structure evolution, we like the PFSS can work well. But if we are interested in looking for the heating, which is happening at very small scales, so in those cases, to associate heating using these PFSS models may not be that reliable, I feel. Yeah. Any other views?
Yeah, I have a different viewpoint on this. The thing is, there are cases which I have seen. I've talked to Pratik as well in several occasions that PFS also sometimes fails in capturing large scale structure in terms of capturing the non-potential structure itself because PFS don't cannot capture those non-potential structure like pseudo streamer itself, which I was showing. Maybe the structures we are seeing are some non, they have some non-potential characteristics and PFSS will fail in that. In terms of global coronal modeling, I think PFSS is very useful. That's what we have seen. But yeah, if you're looking at some case studies where you want to understand the dynamics and everything, I don't think PFSS will work there because of the complexity in the system itself. Like you have emerging flux in the system, and then I mean there are several shared arcade twist in the magnetic field itself. So this kind of complexity cannot be captured by PFSS alone. So that's what I think. I don't know whether we should go for like PFSS is very easy to use. We have a very good Python code base for that. But I don't know. I want to raise the question regarding whether there are other codes apart from PFSS for non-potential field extrapolations which are easy to use or not. I I don't know whether that is the issue due to which people are not very widely using those codes or what could be the possible way to widely use those codes uh, so that I mean we can go beyond the PFSS as well. So if you have some views on that, that would be very useful for the community as well, I think.
Just
Yeah.
to have a follow-up, is the main reason that PFSS is only taking BR, the only the radial, and kind of ruling out all the shear flows, whereas the nonlinear kind of incorporates or considers non-BR components as well. Is it the main reason, or is it just the force-free and non-force-free thing?
Hmm. I think force free and non force free is definitely the reason.
Okay.
And the thing, uh, I mean, I'm not sure about the second thing, but that's a good point actually. We need to explore that as well. Yeah, that's a good point.
Mhm. Yeah, so certainly
Even
there are not many open source and easy to use codes available for non-potential extrapolations. That is true. And that is
Yes,
possibly the main
yes,
reason that, yeah, everybody starts with PFSS firstly. Yeah.
Mhm.
yeah.
Oh, I have one question for Vishwajit as well. So you were mentioning about this slitless spectroscopy. So here, like, so one advantage that we can see is like we get a full field of view. But what are the disadvantages? Like, what are we losing compared to single slit spectroscopy in this?
right. So so in the slitless spectroscopy, we can get like a full field of view, but will not get as high resolution as we can get for single slit. So that is one drawback, but one can design such instrument so that we can get high resolution as well. But that is challenging to design technologically right now. But even with the, I mean, slightly poorer resolution, we can get a good amount of information with slitless kind of instrument.
Mhm. I see. Okay.
I have a
So are there?
question for Vishwajit.
Yeah.
Okay, sure.
Yeah,
Please.
yeah. Vishwajit, I mean, I wanted to ask, what is the temperature range covered by Magix? I mean, you are incorporating DEM with those information. That's why I'm asking what is the temperature and which is covered by magics.
Yeah, for the magics, it is typically 1 to 10 million Kelvin.
Okay, so the question is, what is the limitation in your studies which you showed will have if you don't cover the temperature lower than 1 million Kelvin?
Um, I think I didn't get it properly. Can you repeat it again?
No, so you are taking the full region
Right.
of active region. There are hotter plasma, cooler plasma as well, but your observation only covers 1 to 10 million Kelvin. There are no observation of lines below 1 million Kelvin
Right.
in those regions. So how how accurately we are constraining the DM in that case? That's what I'm asking.
I see. So, only with magics we can only constrain above 1 million Kelvin. So we are not looking into the plasma like below million Kelvin in this case. But if we can combine like AIA with magics, then we can go slightly below 1 million, maybe half a million or so.
Yeah,
But
I'm asking
only
this
with
question
magics
because
we can't go
yeah,
below million. Yeah.
yeah, yeah, I
I mean,
understand.
that is
I'm
one
asking
of
this
the
question.
motivation because so far most of the instrument doesn't have sensitive to high temperature. So the
Yes,
Magix
I
is
agree.
primarily designed to capture the high temperature plasma.
Mm. I'm asking this question because of the fact that suppose there is a multi-thermal structure covering temperature in range of log T equal to 5 to log T equal to 7. And if you are only taking log T equal to 6 to 7, then it it may not able to give you the full picture of DEM at that cases. And I know
Mm-hmm.
Athira have shown with his observation that AIA also does not able to constrain the high temperature plasma in with magics he has shown. So I think we can combine different observation. That's good and well, but we don't get such kind of opportunities every time. That's the question. So, do we need an instrument which can cover this kind of range, or do we need something to explore this range of temperature to understand the temperature and density, or to do the diagnostics, so that we have minimum uncertainty in our parameter which we are deriving. That's what I was thinking about while
Right.
listening to your talk.
Yeah. So, yeah, I mean, designing an instrument which is like covered from very low temperature to very high temperature with a single one is very, very challenging. I mean, we can either design for low temperature or high temperature or specific range. I mean, for Magic's case, the primary motivation to understand coronal heating perspective. So in that case, understanding the higher temperature is much more important than the lower temperature.
What do you think about the Muse and Solar Sea mission? Solar Sea, I'm not sure, but what do you think about Muse? Muse can cover those
Yeah,
high kind of
so
temperatures.
Muse can go like so Muse has three pass band. So
Mhm.
one is like 1 million, one is 3 million, another is around 10 million or so. So
Okay.
it will not give you the continuous coverage, but it has the narrow band coverage for three specific temperature range. So Muse definitely can help understand coronal heating perspective.
Thanks, Vishwajit. Yeah, I see Soumya has raised his hand. Yeah, please ask your question.
Yeah, sorry, I'm just sort of breaking the current discussion. I had a question for
Mhm.
Itzana. This might be a naive question, but given that you're simulating the flares, how detailed, I guess, do you have detailed physics regarding the plasma sheet, the fan? How detailed the physics you are simulating there at the loop top? So
You are
you are
muted.
muted. You are muted.
Okay. I really bad with the English, and I can understand you the question again. And I don't know if you write in the chat or.
Sure, I'll write in chat.
Mhm. Yeah. So in the meantime, maybe I ask a question to you, Sayana. So you studied different dissipative processes, which you included in your simulations.
Yes.
For example, like thermal conduction, radiative losses, resistivity, and others. So out of all these dissipative processes, which one do you think is like the most important for the flare loops?
Okay, in my study, I find out that thermal conductivity is the most important dissipative process because this redistributes the energy along the magnetic field lines, and this um, this puts close to the observations that so
Mm.
in our study this is the most important.
Okay, thank you. And do you think we can also like have some observations which can also validate these kind of studies, like showing role of different dissipative terms separately? Like, can you think of some observations like which can support this numerical study that you shared with us?
Uh, um, for the moment, at this point, we only compare qualitative with the observations because our model is very idealized. We don't have the real magnetic field, so need to implement that for we we are capable of reproduce observations.
Okay. Yeah. Thank you. So Soumya has like posted his question in the chat. Maybe you can have a look, and we can have some other question in the meantime. So so for Jane, I have a question. So Jane, so is there any like from your experience as well as from the literature study that you would have done? So is there any threshold in the magnetic complexity or of the flux rope, or let's say the twist rate or the skewness of the flux rope beyond which like eruptions becomes more likely?
This this study morphology what I did is actually qualitative type.
Okay. Mm-hmm.
That is actually we don't have the coronal magnetic field observation, so we are going for the another type of observation like bar bearing, skewness, and it is cohesion or something like that. So this way we can get only a qualitative analysis. Quantitative we have to simulate the HMI data from the photosphere, or if we have the coronal magnetic field observation, from that only we will get the exact twist. It is kink unstable, or it is going to erupt. It is due to kink unstable or not. Mostly some feature in this time we have seen the filament is going to be erupted, and it is getting reformed, and it is getting again erupted, and one more time we have seen it has a negative ride, and it has a negative helicity. So it has a continuously showing a negative helicity trend all over the time when we have tracked. So this negative trend of helicity in the whole time means that it can have a evolution or emergence of a negative helicity all over the time. So this may leads to the kink instability of the filament, and it get erupted. We final time we have seen it get erupted and leads to a CME. So all this analysis we doing with the qualitative analysis only. We don't have that measurement. So image analysis, we tracked that filament for a long time. So we found its height also, and its helicity we found from there is another method, Chen 2014, they have used. When we have eruption, there is a dropping points is there. So that brightening points and PIL determination, we can have a textile chirality orientation or a sinistal chirality orientation, and this bar bearing and another skewness. All this is matching with the negative helicity trend, and a ride during the eruption we have seen it is a negative. So all things is matching with the negative helicity trend, and finally it get erupted. So this matches with a king instability, may be the reason for the eruption of the filament.
Okay. Yeah, but with, let's say, improved spatial resolution, like, do you think like this spatial morphology of the filaments can work as an indicator of flare eruption?
Like a sheared arcade or a flux rope? Yeah.
Yeah, means the complexity of the filament shape, like, do you think it can also work as an indicator, like a reliable indicator of the flare eruption? Like with current
Yes,
data, I assume that it's not possible. Yeah, but let's say with the improved resolution. Like,
if we in this study we will get a it is like we will get it is negative helicity or positive helicity, that only we don't get a quantity. So that is the issue in this analysis. So we have to track. So one of the filament we have tracked, so we got that idea, like every time it is showing that part. So what ma'am asked, it is this evolution part we have to be analyzed, like in trend it should be analyzed.
okay, yeah, yeah. Thank you, Jane. So yeah, so Itzayana, do you want to like answer the question by Soumya, which was put in the chat? You are muted.
Yes, responding to the question is that we have a big limitation, that is the computational capability. And for this reason, we use a low resolution, and this stopped to see these types of structures like buoyancy instabilities or termination shocks. We cannot see at this moment.
Okay. Yeah. Thank you, Itzayana. I hope it answers Soumya's question. So yeah, so this also brings us to the end of this session, and I would like to thank all the speakers and all the participants for this engaging and wonderful discussion. So over to the organizers for any announcements.
Thank you, Nitin, for sharing the session. It was seamless, very natural and fluent. Ritesh is already here, who is the session chair, the next one, which will start within 10 minutes. Let's just quickly check the presence of next speakers. Ritesh, can you quickly verify if the speakers are present?
I am looking. Akash, Priyansh is there. I think not all the speakers are right now present. Maybe they will join in like close to the starting time.
Hmm.
In the meantime, sorry,
Hmm.
Priyansh, can you share your presentation?
Yes, I can. Let me try.
Priyansh is the first speaker.
Yeah. I think Pratik, you should mute yourself.
Oh, okay. Wait. Can you see the slides?
Yep.
Shall I stop sharing for the time being?
Yeah, yeah.
Okay.
Yeah, I hope they will join soon.
Mm-mm.
So it's late night for Ritesh. It's 11:30 approximately.
It's the same time for you, Prateek.
Yeah, same time for me as well.
Not the same sleeping time for you guys.
Yeah, that's true.
Yeah.
I I I already took one nap.
Hmm.
Ritesh is already sleepy now.
Yeah. I
But eruption will wake him up.
that's
Solar eruption.
yeah. I hope Priyas does a good job of waking me up.
It's actually nighttime for me as well.
Oh no. Where are you?
I'm in Maryland.
Oh, so it's
Oh,
even later. Okay.
even later.
Even later.
But still, I'll try my
Oh,
best.
so Priyansh is already sleeping. That means.
Ah.
Not really.
So we have one speaker lesson session. Like there's one abstract retracted.
Okay. Just a small advertisement regarding the panel discussion, which will happen in the evening session, phase 4. And today's theme is science discussion on space weather and heliophysics. And also, after that, we'll have invited talk on usage of AI or machine learning for, again, space weather. So I hope you guys will join. We have invited, I would say, global leaders, and they have kindly agreed to join for discussion, and high expectations with today's session. This we are quickly sending a reminder email to the speakers.
Okay. Yeah,
I
because
think their plan is to join at the exact moment of their talk.
Mm,
I don't see even Akash Vinod. I see Akash Gupta, but he's
yeah,
different person. Um, so yeah, for now it's only Priyansh.
yeah. So we'll have group discussion starting and ending with Priyansh.
Yeah, we'll start with the group discussion. So Priyansh, are you in the Maryland for any visit or something
Yes,
else?
I'm here for the ESCO visit at government.
Oh, okay, great. Same as name. Your senior, same as your senior,
Yes, yes. It was,
Yoshita.
yep, Yoshita.
Where are you staying there?
Greenbelt, it's nearby to the office only.
Okay.
Are you also working with Nat?
Yes.
Shatabdo just joined. We can put him in the stage and ask him to present something if no one comes.
Ranadeep has also joined.
अब भी
It's
प्रेजेंट
early
करके
morning
दिखा
for
रहा हूँ
Ranadeep.
Both Shatabdo and Ranadeep early morning just
Hmm.
getting up.
हाँ बस सोलर फिजिक्स ही सोचता हूँ रात को सो के तो अभी फ्रेश हूँ बिल्कुल
Oh, that reminded me.
Ritesh, do you think that we should start? Maybe.
We should wait because only Priyansh is there. Second speaker is after him, no one is there.
Do I get 60 minutes?
It's up to you if you want to
No,
be
not
awake
Yeah.
really.
more than.
It will become plenary session then.
Yeah, we can make a plenary session, a special announcement.
And a very reasonable request from Priyansh.
That too at 1:30 at night.
Yeah.
Let's wait 1 more minute and then we can start. Okay, think we can start and Pratik, you let's see if others join in between Priyan's talk.
Yeah, sure.
Okay. Okay. Good morning, afternoon, and evening to everyone, and let's resume our session day 2, phase 2 on solar eruptive phenomena. So our first speaker is Priyansh Jaiswal, who is in the middle of night, and he's going to talk about May 2024 geomagnetic storms. So without any delay, over to you, Priyansh. You have 10 minutes and 2 minutes for questions, and it can extend up to 1 hour, as you know. So yeah, go ahead.
Okay. I hope you can see my slides and I'm audible.
Yeah. Make it full screen.
Okay. Is there?
It's saying loading. Yeah,
Okay.
it's coming. Yeah, it's fine.
Okay, shall I start then?
Yeah, go ahead.
Okay. Hello, everyone. First, I relay my sincere gratitude to the organizers of the ISHA 2026 for giving me this opportunity to present my research work. I'm Priyansh Jaswal, fourth year PhD student at Center of Excellence in Space Sciences India at ISHA Kolkata. Today I'll be talking about the superactive region 13664, the perpetrator behind the May 2024 10th to 11th geomagnetic storms. I did this work in collaboration with Shubhadeep Sinha and Dibyendu Nandi at CC ISHA Kolkata. During 10th to 11th May 2024, Earth witnessed a geomagnetic storm. The DST levels had fallen down to minus 412 nanotesla. It was the strongest storm in the past 2 decades since the 2003 Halloween solar storms, and it makes it very useful for the space weather assessment studies. What had happened? So if we look at the heliospheric conditions during that period, during 10 to 11 May, multiple coronal mass ejections had hit the Earth. So this yellow dot here is the planet Earth, and the center is the Sun, and this is the famous or very nice WSN simulations. If we go to the Sun, and we find that active region 13664 during this period had produced multiple flares, X-class flares, which launched the associated coronal mass ejections. So the CMEs that hit the Earth eventually during the geomagnetic storm period but it launched near around this 8th or 7th May, which you can see in this simulation itself. Luckily, we had this spacecraft solar orbiter represented by this red diamond here under the green spot at the far side of the sun, and we were also observing it from the earth itself. So for the near side observations we have GOES data, and for the far side observations we luckily had STIX instrument observations for the flare on the back side of the sun. So we could map, and we found that there were in total 23 X-class flares produced by this particular active region over 1.5 solar rotation during its lifespan, amongst which there was an estimated X12. Okay, I have a pointer. There was an X12 flare, which was the then strongest flare of the solar cycle 25. First question that we answer in our study is, how extreme were the physical properties of active region 13664? In terms of its foremost physical property, that is the area, active region 13664 had a magnetic expanse of over 4,000 microhemisphere. For a comparative estimate, qualitatively, it would take around 104 Earths to cover this huge active region itself. Statistically, it ranked at 99.95 percentile among the area of all the sunspot groups or the active regions over past 150 years, leaving only 22 active regions which were larger than this particular region out of more than 42,000 active regions. Similarly, over past 3.5 solar cycles, that is about 30 years or slightly more than that, in terms of flux content, the active region 13664 stood at the 99.10 percentile, with only 37 active regions greater than this in terms of flux out of more than 4,000 active regions. Over the SGO era, we look at its multiple physical properties which are available through the SHARP data series. We again find that all the physical properties for this particular active region, which can be calculated from the vector data itself, and some properties from line of sight data also, but majority of them are using the vector data. That is why we limit ourselves to the SDO array itself, where the magnitude of these physical properties was extremely high. And from another study, that is Sinha et al. 2022, we took these parameters which are in gray shading and red text are the top 5 flare relevant parameters. And among these parameters, if you look, there are parameters like total unsigned current helicity, absolute vertical current, and there's a current density is total twist. So these are primarily the non-potentiality markers, the terms where you have curl of B in the formula or the calculation, as the last panel discussion was also discussing whether the NLFFF models or the PFSS models are better and which one should be used. So it's about that itself. The higher the quantity you have for the non-potentiality markers, that basically indicates that you have more pool of free energy, which would eventually tell you if the active region is flare prolific or not. So in total, active region 13664 had extreme physical properties, putting it at the higher end or the extreme end of the spectrum. Second question we try to answer in the study is that why was this particular active region 13664, or also you can say 3664, was super active? This particular active region started as a fairly average active region with very low flux levels, or you can say usual flux levels with Hale polarity in the southern region. Near 6th to 7th May, it experienced rapid flux emergence in its vicinity as active region 13668, which within less than a day coalesced with the 3664 and produced or made up this whole single activity complex. If we look at the temporal evolution of the top 5 flare relevant parameters, we would see that as we noticed in the animation itself, the flux content of the active region initially was low. But during this period, that is about 6th to 7th May, there was new flux emergence which coalesced with the existing flux content, and it made it rapidly rise. Now, during this rise phase, you will notice that other properties also, which are flare relevant, also started rising. Especially if you look at this particular quantity, that is the R value, which is basically the flux content available near the polarity inversion lines, the unsigned flux content, which is a measure of the amount of flux that you have for self-flux cancellation and eventually reconnection. So most of the flare activity, or I would say the strongest or the intense flaring activity, that is the X-class flares, is clustered around this rapid rise phase and the peak. And during the second near transit, when it went back behind the sun and it again came to face the earth, the activity levels, the mean activity levels of the active region had dropped as compared to the first transit, which was endorsed by a fewer number of flares as well. So is it sufficient to have just the energization of system? Will that be enough for producing such intense activity? Answer is not really. There are other factors as well. If you compare 3664 with its predecessor 2192, which was area-wise largest active region in cycle 24, you would see that some of the flare relevant parameters were even higher. The mean levels were even higher for the case of 12192, but still it was not producing as many flares and as strong flares as active region 13664. If we take the magnetogram observations, it will get quite clear. For the active region 1 to 192, we have a fairly simple magnetic topology with its positive and negative polarities separated out, where it leaves you with a very small PIL, that is a polarity inversion line, leaving you with less avenue for self-flux cancellation and reconnection. Whereas for the 13664, it is otherwise. You have this positive polarity stretched in between, sandwiched by the negative polarities from all sides, and it is having huge or longer polarity inversion lines. To sum it up, we conclude that active region 13664 to be a superactive region possessing extreme properties, putting it at the extreme high-end spectrum in terms of its physical properties. Extreme flaring activity is clustered around the peak values and rapidly rising phases in the temporal evolution of the flare relevant parameters, which indicates that the rapid flux emergence or the new flux emergence, which led to the development or complexity, increasing the complexity of the topological topology of the active region itself, produced more avenue of reconnection. Mean levels of flaring parameters reduced during the second near side transit, indicating low flaring activity, which again reinforces the fact that the flare relevant parameters or the properties of active region are very helpful in identifying the flare prolific sites. As a one-liner summary or the implication of the study, it's that our study is important for identifying superactive regions given their potential to generate adverse space weather events, as we experienced during 10th to 11th May 2024 itself. Our investigations support the idea that energization of non-potentiality markers can induce flaring activity, which again comes to the point that the greater the non-potentiality you have, like the parameters of current helicity, total twist, and vertical current, you'll have more pool of free energy. So that eventually measures the amount of flare energy that can be released. Thank you.
Yes, thank Priyansh. Thank you for keeping it in time. Any questions for Priyansh? I see raised hand from Ranadeep. Go ahead.
Hi, Priyansh. Thanks for this
Hello.
nice. So you have compared your study with the active region 12192, and that has produced, like, if I remember, 6 X-class flares, but none of those were accompanied with CME eruption. So all of this were like confined flares. So
Right.
comparing the active region complexity between 12192 and the current active region like 13664, could you comment on that also? Like why this different type of like
Yeah, so as you mentioned that the AR12192 was flare rich but CME poor.
yeah.
So there has been studies on that as well. in our study, we primarily stick to the active region properties, that is using the surface magnetograms, and we do not look at the atmospheric observations in the corona itself. But when it comes to coronal mass ejections, it is very important to encapsulate those as well. If a flare is happening, and let's say there is material in the above the active region in the atmosphere, then there will be a more chance of having CMEs. So just based upon the magnetogram observations, it might be difficult to say if it is eventually going to produce or launch a CME or not.
Yeah, so I guess the main reason was that probably this 12192 has very strong overlying magnetic field that actually suppressed those eruptions. Yeah. So, and another question is to you that when you are studying these different non-potential parameters for active regions, so are you like taking the mean of the whole active region, or also have you looked at to study these parameters in a localized field of view close to the flaring location as well?
So we are doing it for the whole active region itself. We did not try it for the localized position for the flare itself, but that is something one can try.
Yeah, I think that would be interesting as well.
Yeah,
Okay,
that's a good
thank you.
idea. Thank you.
Any more questions for Priyansh? Okay, Shatabdu, go ahead quickly.
Thanks. Hi, Priyansh. Interesting work. I was just wondering that, well, let's say for upcoming more complex active regions in the future, how much difference do you think it would make to have vector magnetograph observations in terms of the parameters that you have talked about to predict whether that active region would be a strong active region or not? Like how important it would be to have vector magnetograph observations beforehand?
Vector magnetogram observations.
Yeah.
So yeah, if you look at the evolution of these parameters itself, which are the non-potentiality markers, when I say that, I need the term curl of B, like to calculate the twist or the current densities or current helicities. If you can track the evolution of those quantities before the flare has started in itself, you would see that most of the quantities they start rising. So once you have enough energization in the system, once you have a lot of free energy available, there is a higher probability of having flares. So yes, having vector observations beforehand is useful in prediction as well.
Okay.
I hope I answered your question.
Yeah, thanks. We can discuss more later.
Okay.
Thanks.
Okay, let's thank Priyansh. And if there are more questions, we can have it in the discussion session. So I see the next speaker has retracted their abstract, and the speaker next to them, Akash, not Gupta, but Akash Shirke, they are also not present. So let's surprise Pawan and ask him to share his slides. So Pawan from Patna University to talk about recurrent magnetic reconnection and QPPs.
Hello.
Yes, Pawan, we can hear you.
Okay. Thank you for giving me this opportunity and thank you for the early surprises. So let me start my slides.
Okay, go ahead. So Pawan, you will have 10 minutes for the presentation and 2 minutes for uh, questions and discussions. So you can start sharing your slides.
So are my slides visible?
Yes.
Yeah,
Can
good
you make
evening
it
and
full
good
screen?
morning, everyone. Yes. Just a second. Sorry, but this will present like this only.
Okay, no problem. You can go ahead like this. Yeah.
Today I will talk about my ongoing work, the role of recurrent magnetic reconnections in X-class solar flare and the associated QP. So this presentation will go like this. First, basic introduction, then observation, and finally I will come to the methodology and the preliminary results of my work. So as we know, since we are working in solar physics domain, so we all know about the solar transient events like solar flares, coronal jets, and coronal mass ejections are hosted by the solar atmosphere of the sun. And this work is solely focused on the flares. So we all know the solar flares are classified in two groups, confined and eruptives. So in this work, I will talk about the eruptive flare, where the coronal mass ejection is associated with the flare. In the basic introduction, when we talk about the solar corona, due to high Landquist number, the flux fusion condition is imposed in the solar corona. So the observed loop-like brightenings are inferred as the magnetic fields. Since we are modeling the solar corona in terms of near ideal condition, like plasmas are near ideal, so diffusion time scale will be large in the solar corona. But we see the transient events which occurs on a time scale of few seconds to minute. So that brings a scenario that there might be some diffusion will induce in the localized region, and this brings the scenario of magnetic reconnection, where we infer that the length scale in the solar corona will decrease like locally, and that will bring the oppositely directed magnetic field lines in closer proximity that will give rise to the magnetic reconnection. So now I come to my work. So we have analyzed a flare that is hosted by Activision 13842 on 3rd October 2024. This flare was initiated at 12:08 and peaked at 12:18, and finally this flare is ended at 12:27. So in this animation, you will see this is the basically cutout of the full disk solar disk where the flare is being hosted. You will see first a faint brightening occurs like sigmoidal brightening, then a sequential brightening develop, and in the snapshot in panel A, you will see there are 4 different brightenings appeared as the flare reaches to its peak. These brightenings are labeled as different names like BR1, BR2, BR3, and BR4. See, associated with these 4 flare brightenings, we observed 4 flare ripples. So, when we investigated the emission of the solar flare, then we obtained the quasi-periodic pulsations in extreme ultraviolet and ultraviolet range. So, in extreme ultraviolet, we observed a quasi-periodic pulsations about 2 minutes, having a time period of 2 minutes, and in extreme ultraviolet case, we observed the quasi-periodic pulsation about 6 minutes. These different periods in different channels of AIA suggest that these QPPs are coming from the different region of the sun, or they are associated with the different physical processes that are giving rise to them. So in order to investigate, since we are investigating a solar flare and basically we will deal with the magnetic reconnection, so in order to investigate the non-thermal emission, we have investigated this hard X-ray spectra, hard X-ray intensity profile observed by Aditya L1. Since the data was available for this flare, so in hard X-ray regime, we also obtained a quasi-periodic pulsations about 1.06 minute. So we are obtaining the quasi-periodic pulsation in 3 different channels like UV, and hard X-ray. So these different channels and the quasi-periodic pulsation in different channels with different periods allow us to say that these quasi-periodic pulsations are coming from different layers of the sun. So in order to investigate the onset mechanism of the flare and the associated QPP, we have performed a sequence of non-force-free field extrapolation using the vector magnetogram. And we construct the initial magnetic topology. Like you will see in panel A, we have 3 different colored field lines like yellow color, green color, and the pink color. These green color field lines are inferred as the magnetic flux rho. As we have checked the twist value and we found the twist greater than 1, so these green color field lines are inferred as the magnetic flux flow, which are enveloped by a pink color field lines. These field lines are generally regarded as the shear arcade, And in order to investigate the topology associated with the yellow color field line, we have projected these field lines in 2D structure, and we found the intersection of two QSLs. Like you will see here and here, these two QSL intersection and a neutral XA point. This allow us to tell that this yellow colored field line is inferred as the hyperbolic flux tube. And these three magnetic topologies are highly are the potential sites considered for the magnetic reconnection. So, since we have performed a sequence of extrapolations, so we tracked the evolution of the magnetic flux flow with the twist. So, in the first panel, you will see the magnetic flux flow has some kind of twist here, and this twist is increased at with the advancement in time before the peak of the flare, and the right part of this flux loop is found to be raised. And after the peak of the flare, we found the twist decreases to a value 1. Then this make a sense that the twist in the green color field lines is disappeared. That suggests the eruption of the magnetic flux loop before the onset of before the peak of the flare. And in order to investigate the eruption conditions, suitable condition for eruption, we have plotted the decay index, and we find in the region above the flux loop is torus unstable because this have a value of decay index 1.5. So we have plotted the height of the flux loop with time, and we found the height of the flux loop is increasing with time. And also in this slide, you will see above the flux loop, we have a torus unstable region that help the flux loop to erupt. So, in order to check the possibility of magnetic reconnection in HFT structure, we found that as the time advances, this HFT structure is formed. So, coming to the previous slide, when you will see, hello, am I audible?
Yes, yes. Go ahead.
So, if we move to the previous slide, then you will see the height of magnetic flux loop increasing. So this allows us to assume a condition that the height of magnetic flux loop increasing by stretching the field lines of the shear
Pawan, I think
help
it's
to generate
okay.
it's frozen. Hello.
You broke for a second, but now we can hear you fine.
Okay. So as the flux of height is increasing, that will stretch the overlying field line that the shear arcades, and this will so by assuming these conditions, you will see we have plotted the field lines over the AIA observation, and you will see the location where the shear arcade was present, which maps the sigmoidal brightening that was appearing first. So this infers that the shear arcade will constitute high electric current, and that high electric current will bring the joules hitting into the play, and that will give rise to the sigmoidal brightening. Later, we observed the magnetic flux of the twist in magnetic flux of was increasing. That is suggestive of the reconnection in shear arcades, and these reconnection in shear arcade will give rise to the two brightenings like this and this. So these two brightenings are mapped with the foot points of shear arcade. That is suggestive the reconnection in shear arcade happens, and later the reconnection in HFT structure, the accelerated the charge particles along this direction and it hit this solar surface to give rise to the third brightening here. Also, the reconnection in HFT will accelerate the charge particle along the fan of the HFT, and that will hit the solar surface and give rise to the circular brightenings here you can see. So associated with these four brightenings, we observed four different flare ribbons, and those flare ribbons are also co-spatial with the flare brightenings. So finally, we conclude our results that we have different topologies in the flaring region like shear arcade, magnetic flux tube, and hyperbolic flux tube. And these hyperbolic flux tube and shear arcade reconnections are giving rise to the flare brightenings and associated polyperiodic pulsations. So, thank you.
Thank you,
These are the
Pawan.
preliminary outcomes. Hello. Yes.
Okay, Any questions for Pawan? I see Priyansh. No, that was clapping. If not, then I have one question. So the extrapolations that you showed, uh, I may have missed it. Is it non-linear force-free or non-force-free?
No, no, actually it was non-force free.
Okay, okay, thanks.
Yes.
Uh,
Like here I have shown this non-force free model.
okay, yeah. Okay,
We may
if
have one
there,
quick question to him. Sorry.
okay, go ahead, Randy.
Yeah. So you mentioned about the torus instability. So could you comment on that? What is the decay index you got at the eruption height, or if you got the eruption at all?
Okay. Yeah. Let me share this slide first. Here you will see. I hope the slides are visible.
Mm-hmm.
Here you will see, since the torus unstable region, like generally marked as the critical value of decay index, that should be equal to or greater than 1.5. Okay. So in this just above the flux flow, we have plotted the decay index and we find the decay index value is increasing from bottom to top. Okay. So and the as we move from bottom to top region, the critical value of decay index is approaching to 1.5. And in the next slide, I have shown that we found the flux of height is increasing with time. So based on this observation, I am saying that the flux slope is rising under the favorable condition. And once it will reach the value of decay index 1.5, that is basically the critical value for the torus unstable region, then it will get it.
Okay. Okay, thank you.
Okay, if
Thanks.
there are further questions, then we can take up in the discussion session. Let's thank Pawan again. Our next speaker is Karthik from University of Turku, Finland, and he's going to talk about radio burst and the properties of associated shock waves. So Karthik, you can share your screen.
Hi. Yeah, I will try sharing my screen.
And you have 10 minutes for the presentation and 2 minutes for the questions.
Is my screen visible?
Yes.
So it's in the PowerPoint, right?
Yeah, slideshow mode.
Okay, perfect. So hello, I'm Karthik. I'm doing my PhD in University of Turku, and as previous speakers talked about various energetic eruptions, I'm going to talk about one of the phenomena that are associated with this energetic eruptions, which are the shock waves. So these shock waves are often associated with when there's an eruption happening in the solar corona. So type 2 bursts, the one that I'm interested in, are associated with the shock waves. More specifically, they are associated with they're generated from.
Karthik, we cannot hear you, I think.
Somo, I can hear him.
Hello.
Yes, Karthik, I can hear you.
Yes, we can hear Karthik. Yes.
Okay, great.
Maybe
Yeah.
it's Somo side. Yeah.
Yeah, maybe it's PRL internet.
Okay. Yeah, that's good to know. So continuing, so these shock waves, what they do is when they accelerate electrons, and these accelerated electrons, they they convert the energy into Langmuir waves, and they convert into they emit the electromagnetic radiation in the form of type 2 burst, which you can see here in this dynamic spectrum. So moving on, one of the key properties of these shock waves is that they have a rather slow drift rate in the dynamic spectrum, and they are emitted generally in harmonic and fundamental bands. each of them have both of them have a frequency ratio of roughly 2. So these type 2 bursts are what we call the plasma emission, meaning that the emission frequency is inherently dependent on the plasma density around the shock waves. So in here you can see the type 2 harmonic band, and here is a little fundamental band, and they have a frequency ratio of 2. So moving on, the aim of my study is to do analysis on multiple type 2 bursts and try to find some of the key parameters such as Alfvén Mach number and the angle between the shock normal and the magnetic field line. And both of these quantities are essential to determine the efficiency of electron acceleration. So our goal is to determine these quantities. So as a part of this discussion, I'm going to present the analysis done on one such type 2 burst. A similar analysis has been done for the rest of the 9 bursts. So here is a type 2 example type 2 burst, which occurred on 29th of May 2024, and it was observed by multiple instruments, and it was associated with the limb CME, which was observed by SDO, Stereo, and other spacecraft as well. So it was also accompanied by an X1.4 class flare. So this CME was associated with a shock wave. So what we do is we fit this shock wave with a simple spherical model and propagate it across time. So what this gives us is the shock speed at different directions. And so moving ahead, we look at the radio images of these type 2 bursts. So these are the radio images at NRH, an unsafe radio heliograph frequency look like. And we track these, we fit this radio burst with a Gaussian and see to determine the locations of these radio bursts. Now we have the 2D locations of these radio bursts. So moving ahead, what we do is we use the simulation model called MAS, which is developed by Predictive Science Inc. So what this gives us is it takes in the photospheric magnetic field from SDO, and it spits out the coronal electron densities and the magnetic field around in the corona. So what this allows us to do is derive some of the key properties such as Alfvén speed in corona and even the magnetic field lines, how they are propagated in the corona. So moving ahead to the results, what we get is there's a lot to unpack in this image. So what we are looking at is a density isosurface. So this is a constant density surface, which is associated with the 150 megahertz harmonic type of emission. And these are the radio sources which were deprojected using the density isosurface. And what we see is they lie in the region of low Alfvén speed. So the density surface is overplotted with has the color map defining showing us the Alfvén speed on the surface. So what we notice is these radio sources, they lie in the regions of low Alfvén speed. So just to say that, and they're often found really close to these magnetic field lines, the closed magnetic field lines, which are low coronal counterpart of the streamers which we observe in coronagraphs. Moving ahead, what we do with the shock fitting, which I explained in the previous slide, so this here is the shock fitting, the red and white colored bubble. So what we overplot it with is the theta BN angle, the angle between the magnetic field line and the shock norm. So here what we do is we determine the theta BN angle around these radio sources. So this was about the analysis done on one such event. We repeat this analysis for 10 different events and find that what are the key things that we find is that all these radio sources that are associated with the right to bus lie in the region of low alpha speed. And also, what's interesting is that they lie very close to these closed magnetic field lines, which is kind of interesting. And this magnetic magenta mesh tells the shocks that were fitted for these events. Moving ahead, we also find the theta PN angle for all these events. And what's kind of interesting is that these radio sources, they lie in the regions of low theta PN angle, which is opposite of what we expect. So in the shock acceleration, it is expected that the angle between the shock normal and the magnetic field, the theta BN angle, should be really close to 90 degree for efficient acceleration of the electrons. This is not what we observe in our study. So what we see is that they're usually in the regions of low theta BN angle. And what this suggests is that the shock waves are generally have a rather complicated surface than a simple sphere, meaning that they can have these undulations in the surface, which can generate regions of quasi-perpendicular nature, resulting in electron acceleration. So here's the result that we get for these events. So what's key things to notice is that the alpha Mach number and fast magnetosonic Mach number are quite high. They are higher than what's called the criticality of the shock waves, which is around 2.3 for quasi-perpendicular shocks. And what we see is all these numbers, they exceed 2.3, meaning that all these shock waves mostly are supercritical in nature. And the second thing to notice is that theta PN angle is not always close to 90. Apart from this event, we always find that they are quasi-parallel or oblique in nature, hinting at more complicated structure of these shock waves. So those are the key conclusions that we get. Yeah, thanks.
Thanks, Karthik. Time for questions for Karthik. You can raise your hand or you can type in the chat box. Okay, Ketaki.
Yeah, Karthik, this is Mahendra.
Oh,
Yes.
okay, Mahinder. Yeah, go ahead.
Can I ask question?
Yes, go
Sure.
ahead.
Yeah, so nice talk, Karthik. So I have a question regarding the fundamental line harmony.
Mhm.
Why the harmonic strength is more than the fundamental? What you have shown the first figure. The
This
strength
is
of
not.
harmonic, yes, the strength of harmonic is more than the fundamental. What is the basic reason behind that?
So they're not usually the case, actually. There was a study published recently which compared the intensities of these fundamental band and harmonic band. It was found that for limb, the events that are close to limb, the harmonic emission is usually stronger. But again, these are linked to the scattering effects, meaning that the fundamental bands, the fundamental band undergoes more scattering in the solar atmosphere, whereas the harmonic band just passes through it.
So, and also the reverse process also there. Sometimes the fundamental is stronger than the harmonic.
They've also been observed. So that's what I said. It's not usually the case. It's just for this event, and most of the metric type 2 emission, we see the harmonic emission being more
So you
intense
are
than
working
fundamental.
on the only
Mahinder,
metric.
sorry, Mahinder, we can take more discussion in the discussion session after the talks are over. So we can have
Okay.
more on this, right?
Yeah. Okay.
Because we have another question
Thank you.
from Ketki. Yeah.
Yeah.
Yeah, thank you, Karthik, for the nice talk. I wanted to ask about on the speeds that you calculated from white light observations and from radio observations. So I saw that you have assumed that it's a spherical shape of the shock. And I wanted to know, you have like statistical studies. So I wanted to know like where this like shock signatures were generated, like at the flank or at the nose of the CME, and how the interpretation of the velocity then is compared with the white light observations.
We use white light observations to determine whether where the nose of the shock wave is.
Yeah.
And these type 2 bursts, they generally are like close to the flanks. Not all the time, of course.
Yeah.
So what your question is your question how we determine the shock speed?
Just the interpretation, because if the shock is not always at the nose of the CME, and if it is generated at the flank, then, and also you are considering a spherical shape of the shock, which is not the real case, right? And if you are assuming the spherical shape, then you are just calculating the radial distance at the flank and at the nose of the CME, which will be almost the same. So I just wanted to know how you interpreted that.
Yeah, like you said, it's not usually it's not usual that the shock wave is very nicely visible in the VR white light images. We do like we generally have to work with what we have. Sometimes there's a half shock wave sometimes. And especially for the shock reconstruction, we generally use these tricolor AI images, which further enhances the shock the shock that is visible, the visibility of the shock. So this is what we use. As far as the question is concerned, I think we just use what we have.
Okay, thank you.
Yeah.
Okay.
I
Thank
hope
you,
I was
you can unshare, and there is a question in chat that you can answer it there. Meanwhile, we proceed to our next speaker, who is Dr. Sarkam Mule from University of Glasgow, and she's going to talk about QPPs and solar flares. Over to you, Sarkam. You can start sharing.
Can you see my screen?
Yes.
Okay, thank you. So, hello everyone. I'm Dr. Sargamule. I'm a postdoc at University of Glasgow, and I work with Professor Lindsay Fletcher. Today I will be talking about the quasi-periodic pulsations in solar flares, and we used iris observations to study them. So quasi-periodic pulsations, these are the most commonly observed phenomena in solar flares. These are the intrinsic part of the flares, and they often exhibit periodic fluctuations in observed radiation. So here I'm showing you an example of quasi-periodic pulsations observed in GOES, and we have taken the derivative of GOES to see them clearly in two different journals of the GOES. On the right hand side, I'm showing you a table which highlights the information that they derived using different instruments. So they studied the periodicities using GOES, Fermi, RACI, also IRIS observations and radio observations as well. So the periodicity is typically between 7 and 250 seconds in case of solar flares. The likely cause of this quasi-periodic fluctuation is the time variability in charged particle acceleration process, and that might be due to quasi-periodic magnetic reconnection. And there is a QPB catalog available in the University of Warwick website if someone is interested. So this is the overview of my presentation. So I would like to talk about the quasi-periodic pulsation that we observed in M7.3 flare that was observed on 18th of April 2014. So here I'm showing you AI field of view, and the red patches over here, these are the solar flare ribbons. So we have observed only one of the flare ribbons in iris field of view, and this is the iris field of view here shown in black box. This is a zoomed view of the iris, and you can see the slit jaw imager 1400 Armstrong that observed only small part of the southern flare ribbon, and this is the iris slit position where it captures emission from this part of the solar flare ribbon. So the objective here is to study the quasi-periodic pulsations using various different lines in iris. So to study them as a height-wise distribution of this periodicity, and also investigate whether there is a change in the periodicities during the impulsive and decay phase of the flare. And we are also interested in studying whether there is a change or the similarities between the QPPs if we see them in different parts of the solar flare ribbons. So for these objectives, we have studied QPPs using wavelet analysis. So we have taken into account various different lines in iris, such as molecular hydrogen, oxygen 1, carbon 1, silicon 4 and oxygen 4, and we also used slit jaw images in silicon 4 and carbon 2 to study them. So we are interested in only this small part of the solar flare ribbon where the flare ribbon was nicely captured in iris slit position. So I'm showing you a zoom field of view of the slit jaw imager here, and these two are the spectral images that we created in silicon 4 emission. So these spectral images are basically the integrated intensity within the wavelength range where we observe the silicon 4 spectra. So I'm going to play the movie. You are going to see the flare ribbon over here, which is going to travel in the downward direction. That means it is going from north to south, and this green line over here is the time for the slit jaw images. As the time passes, you are going to see this green line is going to move in this particular direction, and the emission which is captured at the iris slit location, so you are going to see the evolution of that slit, and you will be seeing this particular sawtooth pattern that is coming from the flare ribbon itself. So I'm just going to play the movie. So you can nicely see the flare ribbon moves, and at some point it just stops, and then you can see there is some kind of small cell structures. They are moving along the flare ribbon, and they also produce the sawtooth pattern in spectral images. So we created these spectral images in various different lines, such as in transition region using silicon 4 and oxygen 4, in the chromosphere using carbon 1, oxygen 1, and molecular hydrogen that is coming from temperature minimum region. On the left hand side, I'm showing you the formation height for this UV spectral lines, just to know that molecular hydrogen is coming from the deep layers of the solar atmosphere. So we are actually probing various different solar heights in this particular observation. So this is the contribution function for the iris lines that tells us the formation temperature of these lines. So interesting thing here is to notice the sawtooth pattern that we have seen in silicon 4 that appears in various different layers. So you can see them in very nicely in these spectral images. So we studied them using the wavelet analysis. So we have taken the intensities along this solar flare ribbon. So this is the light curve, and this is the detrended light curve for this. These are the power spectra we have got from the wavelet analysis. So it gives us information about the time slot. This is during the impulsive phase, and this is during the decay phase of the flare. So from silicon 4, we identified two different periods during the impulsive phase of the flare, around 50 to 80 seconds, and between 120 and 180 seconds. And during the decay phase of the flare, we have seen the periodicities were around 80 to 120 seconds. So we have carried out the similar analysis for various different lines in different layers of the solar atmosphere, and these are the results. So I'm showing you results from silicon 4, the lines from the transition region, and from the chromosphere carbon 1 oxygen 1, and from the temperature minimum region from H2. So this is the graphical representation of the periodicities and the times where the periodicities were appearing at different heights. So let's look at the molecular hydrogen. So in the deeper layer of the atmosphere, we have seen during the impulsive phase and the decay phase, the periodicities were between 80 and 180 seconds. In the chromospheric part, during the impulsive phase, we have seen the periodicities were between 100 and 180 seconds, and during the decay phase, it was between 80 and 180 seconds. In case of silicon 4, we have seen two different periods in the impulsive phase between 50 and 80, and also 120 and 180 seconds. And during the decay phase of the flare, in silicon 4, the periods were between 80 and 120 seconds. In case of oxygen 4, we have seen three different periods during the decay phase, around 50 seconds, around 180, and 180 seconds as well. So interesting thing here is to note that along the y-axis we have periods, along the y-axis we have periods, and along the x-axis there is a time. So if we plot the periodicities, we can see that the silicon 4 and oxygen 4, they are near simultaneous, and also the molecular hydrogen emission during the impulsive phase, but there is a time delay between the emission that is appearing in the transition region and the emission that is appearing in chromospheric lines. So we don't know the reason behind this at the moment, and we are still looking into the physical interpretation of these results. Further, we were also interested in looking at whether this sawtooth pattern we have seen in the spectral images, whether that is there in the other parts of the flare ribbon as well. So we have taken into account the iris slit jaw images. We have put the artificial slit just before and after the iris slit position, and we created the time distance plots. So we have seen this nice sawtooth pattern, same as the spectral images in the silicon 4 slit jaw images, and these are the time distance plots for the on the left side of the iris slit, and this is on the right side of the iris slit. So similar to slit jaw, similar to the spectral images, we have done the analysis for the iris slit positions as well here, and we have obtained the periods. On the left side of the iris slit, we have seen the period was between 100 and 200 seconds, and as you go away from the slit position, the period was around 60 and 200. On the right hand side, we have seen two different periods during the impulsive phase and during the decay phase as well. That was between 80 and 180 seconds at two different locations. So we have compared our results with the results from Browsius and Daw in 2015. So they studied this same flare using 3 different lines: silicon 4, oxygen 4 and carbon 1, and they have seen the periods in the impulsive phase that was around 170 seconds, and during the decay phase that was around 90 seconds. So these are the intensity images they have obtained in different lines. So you can see that they have differentiated these pulsations in the long quasi-periodic and short quasi-periodic. So the first 4 weeks are long quasi-periodic here, and the last 3 were short quasi-periodic. So based on their results, they only focused on 2 different pixel positions along the slit position, and they have obtained this integrated intensities. So based on this, they have concluded that there is a bursty coronal reconnection that is followed by energy injection into the chromosphere by the accelerated non-thermal particles. So the same event also studied by Brannan et al. They studied the silicon 4 emission, and they only focused on the sawtooth pattern that was observed in silicon 4. They have created this Doppler maps to see how exactly the emission appears here in the Doppler velocities. So you can see there is an alternate red and blue patches along this various different parts of the flare ribbon. So from this, they have obtained the periods around 80 and 190 seconds. So based on their results, they proposed a scenario that takes into account the overlying field lines. So we have a reconnection region over here, and they assume that there might be a gauge instability or the tearing bore instability that is appearing in the current sheet during the reconnection, and that might be driving the sawtooth kind of pattern at the flare ribbons. So basically the plasma instability stays at this particular location, and that might be resulting into the movement of this particular magnetic field line that is causing the elliptical motion of the field lines. So we are looking from this particular angle. So this is the small region over here at the foot point of the loops, and this is the zoomed view of that particular region. So we are looking from this particular region. If the field line is going away from the observer, then we are likely to see the red shift, and if it is going close to the observer, then we are going to see the blue shifts. So because of this particular movement of the field lines, there is a possibility of having this alternate red and blue patches in the Doppler maps. So based on this proposed scenario, they observed the oscillation period around 70 and 230 seconds. So just to summarize my results, so we observed the QPPs at various different heights using iris observations in the temperature minimum region, chromosphere and transition region. The quasi-periodic pulsations are spatially and temporally. To some extent, they are correlated at various different solar heights. We have obtained the periods in Slideshaw around 60 to 200 seconds, and also there were other periods at the location of the hard X-ray sources as well. That was around 80 to 120 and 200 to 300 seconds. From iris spectral images, we have seen the periods were between 50 and 180 seconds, and in the chromosphere and temperature minimum region, the periods were very similar, between 80 and 180 seconds. So our future work involves the investigation of the spectral line profiles. So we are going to focus on these silicon 4, oxygen 4 lines and other lines in the solar atmosphere to check if the explanation provided by Brannan et al., which is consistent in various different layers of the sun, and if there are any similarities or differences in the Doppler velocities as well. And we are also interested in studying the small scale structures along the flare ribbons, and we are collaborating with Malcolm Druitt at the University of Sheffield to learn more about this particular type of the event. Finally, I would like to thank IRIS team and I would like to acknowledge financial support from UKR ISTFC. So thank you very much for your attention. I'm happy to take the question.
Thank you, Sargam. So we can have a couple of very quick questions for Sargam. So please raise hand if you want to ask question.
Hello, this is Pawan this side.
Okay, Pawan, go ahead.
Actually, I have a
Pawan, we cannot hear you. I think Pawan has some connection issue. Maybe we'll come to him again. Any other questions for Sargam? Pratik, you unmuted.
No, I was saying that maybe Pavan can write in the chat.
Yeah, that's right. Like Pawan, if you have connection issue, you can also put in the chat. Oh, I think he disconnected his audio. Okay, Sargam, meanwhile, okay, Pawan is back. If you don't hear, I had a question like in this future work, you mentioned small scale structures. So what are those, like the kernels or any other structures?
Yes, so I showed you here earlier the movie. So we can see along the flare ribbons there is some kind of small jet-like structure. We call
Okay.
them as a riblet. So basically, whenever this particular sorted pattern occurs, we actually see that this riblet kind of structure, they actually move across the iris slit position, and you can see there is a brightening, and then there is again faint emission, and then again there is a bright emission over here. That might be because of the riblet structure which is moving through this slit positions. So we are
Okay.
still learning more about what might be the cause for this particular, because it is not everywhere along the flare ribbon. It only appears in particular time of the flare, and that's before the peak of the goes peak. So we are more interested in learning more about why they are appearing at that particular time just before the peak of the flare.
Okay, thank you. Pawan, do you want to ask your question? I think there's still an issue. We can take his question during the long discussion session. So let's thank Sargam and all the other speakers of this session. And is I missed. Is Akash available? Not the PRL one. I don't see him. So okay, we have already thanked everyone. So I think we can move to the discussion session. Get my feelings. Discussion sessions. Yes. So we had a couple of questions that were already answered, and I believe there are many other topics that people want to discuss in this period. So it's an open floor, and whoever wants, they can raise hands and probably direct their questions to the speakers. Sargam, you have a question in the chat already, so you can start maybe directly.
Okay, so it's a question from Sandeep Dubey, and he's asking about how do you explain different periodicities in a given spectral line, that's silicon 4 during impulse EM decay phase. So I think the periodicity is appearing in the intensity in silicon 4, and also there is a periodicity associated with the space as well. So space meaning that at what time or how frequent is the pixel illuminated in silicon 4 spectral images. That is also there. So we are looking into the spectral properties of the silicon 4, whether there are any differences. So for example, in terms of silicon 4 has a very broad profile during the impulsive phase. So not only like one particular Gaussian is enough to fit the line. So we have multiple components that is associated with this line. So we have a stationary component, and we have sometimes the moving component in the red wing of the line as well. So there is a possibility that all these intensity fluctuations, they are not only coming from the stationary component of the line, but there is a contribution from the moving component of the other Gaussians as well. So we are still not sure about like how do you differentiate between why these particular things are happening during the impulsive phase, and whether that has any periodicity effects as well. So we are still looking into it. Another question is about how do you decouple the already present chromospheric oscillations from the QPP relation oscillations. I'm not sure about this question. If Sandeep can explain.
Can you hear me?
Go ahead, Sandeep.
Okay, so yeah, the second one is more related to if you see the chromosphere in a quiescent time, you already have 3 minute and 5 minute oscillations, right? 3 minute is the dominant one,
Mm-hmm.
and then a flare happens, and then you have this QPP induced oscillations that you see in different lines. And the period that you are mentioning are mostly 120 seconds, 100 seconds, so which is close to 2 minutes.
Yes.
So how does this
So, so when we say it's 3 minutes, as far as this particular flare event is concerned, I wouldn't say it's only one particular period, because I can see there is a range of periods that are associated with the QPP event. So in terms of answering your question, how do you differentiate between the chromospheric oscillations? I do not have answer for this at the moment, because we do not have any observation to confirm observation just before the flare to confirm that whether there was chromospheric oscillations already there at the flare location. Whether that also gives us information about 3 or 5 minutes oscillation, and whether we can say that okay, there is a similarity or differences between before the flare and during the flare. But I can look into it. I don't know much about the chromospheric oscillations, but yeah, thank you very much for the question.
Thank you.
Okay, Mahinder, you had some questions for Karthik. Maybe you can ask them now. Is Mahinder online? Yeah,
Yes,
please.
yes, yes.
Yeah.
Yes, Karthik. Yeah. Yeah, Karthik.
Karthik, you are muted.
Sorry. Yeah, I found an article
Yes.
where they discuss about the relative strengths of the fundamental and harmonic
Yeah.
emissions. So I'm gonna
Very.
post the link if that's okay. Yeah. So as I said, it's what one of the key results they found in this article is that the events that occur that have a longitude greater than plus or minus 75 degrees, they tend to have more intense harmonic emission than fundamental one, and also the vice versa. So it's not completely understood why it happens with the metric type 2 emissions. So it's, I think it's still under debate.
Yeah.
So I don't exactly know either.
Okay.
I hope
Okay.
that answer your question. Probably not.
Yeah, it's okay, Karthik. I can take it.
Yes. Thanks.
Okay, Pratik, go ahead.
Yeah, I have a question for Priyans. Not a very specific one, not directly related to what he presented, but since it's a discussion session, I thought to raise it. we know that solar flare forecasting is a big problem. Thousands of papers, but we have not still kind of figured out what are the main features which lead to the kind of eruption. So from your this study, do you have any better understanding or a clear or clarity that what's the current state of the art, where we are right now in terms of this understanding of eruption?
Um, as you said, it's still not decided like which particular parameters, if you like cherry pick, let's say 3 or 4, will those be enough? So I cannot specifically answer that, like which parameter will be better. But if you want to figure out the flare activity, it's best to look at the non-potentiality markers, as I repeated in my presentation also. The one which gives you a direct measure of the free energy pool of the active region configuration. And for the flare prediction problem in itself, it's still an open problem, and still there are multiple papers coming out for the tackling that using AI ML. Now I think there are even papers using the large language models, LLMs. They simply give the full disk images and ask that how it is going to behave in the future. There is a recent paper by a Chinese group. It's called, I think, J1 flare something prediction. JW flare prediction. That's all.
I have also recently read a study in which they asked something from the LLM without giving any data, and LLM gave a report without any data. So that LLM is doing anything, that's fine. But do you think that if we add anything on addition to the sharp data, like EUV images, do you see in the literature on your own study that it helps consistently or not? Means, should we use additional information like EUV intensity maps or not?
Yes, so definitely we should use more data or information because the problem is yet to be solved. And we stick to sharp parameters primarily because it reduces the dimensionality of the full images of the active region or the disks, and it also constrains the input in a way that we understand how active regions or the flares work. So a better way or a more general way would be to directly give the whole image of the active region itself to the model and let it figure out what particular feature from that image is useful for flare prediction. It then again may or may not be a physical property the way we understand the active region. As you said, like it can be anything. But adding to the parameters by magnetogram images and also the extreme ultraviolet images, which is the atmospheric observation, I think that will definitely give new insight to the prediction problem and might improve the results, but the competition cost is going to be very heavy for that. I've personally tried that for the only the magnetogram images, not the atmospheric images, and that also costs a lot.
Okay. Maybe Satabdo has something to add.
Yeah, exactly. Thank you, Pratik, for floating up this topic actually. And I have something that is kind of a follow-up. So what I was thinking about is about forecasting solar flares. So do you think it is, or where do we stand about forecasting, erupting filaments from the quiet sun region? Like, is it easier than predicting a flare in an active region, or is it more difficult because we do see a lot of big filaments erupting from the quiet sun regions? So do we? And this question is not just to Priyansh, and I think this question is to everyone in the Zoom room. I don't work in this area. I was just curious about this topic. That can we predict erupting filaments?
Usually, the filaments also occur near the polarity inversion lines, if I'm not wrong about it. And it becomes more of an atmospheric phenomena. I personally don't have much knowledge about it, so I cannot correctly comment about it also.
Yeah, solar flare eruption and filament eruption, I think, are totally two different problems. totally different data set. I think Hema Priya works on that. Have collaborated also with the Aries people, I think, but still not very clear understanding uh, of the filament eruption as well as its association with the flare. That if flare happens, whether CME will be out or not. If CME happens, flare will be there or not. So those kind of things. So I don't think there is any clear understanding, and I believe the reason is the quality of data set. The number of times of non-occurrence of solar flare, very imbalance of data set, and very non-linear and complicated thing. I kind of always hear this as a joke that when anybody in solar field is starting machine learning, they start with solar flare prediction. So there are many papers, but no clear understanding of that.
But then, how many papers do we have for predicting a filament? Do you have any idea?
Relatively very less, I think very
Less,
less.
right? Yeah. Because I was thinking, I mean, we do have a decent understanding of their magnetic structure for filaments, but I don't know where do we stand on the understanding of the destabilizing mechanism. Yeah.
Surya can be a good thing for that, for filament eruption. A large database, very heavy model, foundation model. I think you can try Surya for that if you are interested.
Okay. Okay. Thanks.
Pratik and Arpit has got good training about
Actually,
Surya.
when we talk about the filament eruption like predictions, so it is not possible to predict for so far the studies. So I have studied. So it is not possible to predict that if you have a filament, like if you have a filament with just above the polarity inversion line, so it will get erupt or not. One thing we can do, sometimes you have a filament, and after the eruption or after the flare, it will have a filament in a particular region and you want to check that it erupted or not, then one thing you can do, you can just check the eruption criteria like fluorescent stability and not. Then I think you can say like this will be erupted or not. But just like seeing a filament by observation, I don't think that one can comment that it is this will erupt or not.
Okay.
Yep.
One thing I would like to add to the flare prediction problem. There are, you can say, not 100% accurate models as of now because always some error will be there in prediction. But there are pretty accurate models. One we have at CC itself, it was developed by Shubhadeep Sinha primarily. So the model is being actively used for generating forecasts as well. It's not only in the like coding aspect, but it's also like have been implemented as a prediction tool. So the results from it is that almost never it has produced a flag which says that active region is not going to produce a flare, and it has. So that will be a false negative. So many of the models also kind of get biased in the sense that they will label most of the active regions in the sense that it will be flare productive based upon the physical properties. But as you all said also, like it's not very clear like which particular features will do the thing. So yeah, that's still debatable, or the problem is still open. Thank you.
Arpit has said something or asked something. Again, in the solar flare prediction direction, what are the bottleneck? Maybe Arpit, you can read Enrico's paper, which has recently published on the benchmarking the Pepsi predictions of last few decades, which is yeah, Ketki has raised.
Okay.
Yeah, I have a different question, so I just want to
Oh,
change the
okay,
topic of
okay.
discussion, I guess.
Yes.
But I have a question to Sargam. Um, we know that radio emissions are also associated with QPPs, right? So I just want to know, like, generalized answer that how they are different from the diagnostics that we do with the UV spectroscopy, and what is the difference between the two, and how they are complementary to each other. You're muted.
Can you hear me?
Yes.
Yes. So if I understand correctly, I showed you that the table in the beginning, and so the most of the periodicity is coming from GOES, Fermi, and many other instruments, including the radio observation. They all they are all are based on the wavelet analysis. So in terms of differentiating between the radio and UV, I would say that there are limitations in terms of understanding, okay, where exactly the QPPs are occurring. So for example, if we look into the chromospheric lines and coronal lines or truncheon region lines, so it depends on when exactly you're looking at these particular radiation. So during the impulsive phase of the flare, so even though we are saying that, okay, they are appearing at different heights, so it will be very difficult to understand the height information here, because from the 1D radon simulation of flares, we can see that during the impulsive phase of the flare, the entire atmosphere is shrink in a very smaller heights. So there might be very small differences in the UV radiation that is appearing from, let's say, chromospheric carbon 1 line and silicon 4 line. But like to connect them with the radio observation, which are coming from very higher heights in the solar atmosphere, so there are limitations in terms of radio observation as well. Like how do you get the height information from radio? That's based on the electron number density as well.
Right.
So I mean, it will be very difficult to link between both of them, saying that, okay, at this particular time and location, we are seeing QPPs in UV, and maybe the times are same in both of these observation in UV and radio, but the location is very different.
But the physics behind it is completely different, or
Completely different. Yes, completely different.
okay. Thank you.
Okay, I have a comment for Sargam. So you mentioned about the riblets, and recently Arpit, I, and a few others, we submitted a paper on UV riblets with solar orbiter. But since solar orbiter, we didn't have the spectral resolution with SPICE. But we will be very much interested. So what results you get? So keep us updated, or we will poke you that what you find out, because with UV we could just see the morphology and speed kind of characteristics. So to look at the spectral information will be very nice.
Yes. Okay. Thank you very much. Yeah.
Okay, Ketki, any more questions? I see your hand is still raised.
Sorry.
So Arpit had a question that is still relevant to solar flare prediction. Like, what are the bottlenecks? My words are getting messed up. What are the bottlenecks right now in the solar flare prediction? So it's a open question to the community, because we know that there are many models, whether it's theoretical, physics-based, machine learning, but still we are far away from predicting when a solar flare and how strong the solar flare is going to be. One thing that I have realized from my personal experience with high resolution imaging is that uh, the underlying phenomena reconnection is happening at multiple scales, and the more the better instruments that we are getting, we find that at Cornell Heights, at least, that I can say that there are unresolved structures which our global models are may not be capturing. So that can be one of the bottlenecks. Others can chip in and point out their view. Pratik has mentioned some comments on
Yeah, I
this.
can reiterate the same thing. When I worked on this, which I worked very slightly, not much. I'm not an expert of this, but what I realized is that there is a huge data imbalance. Means many active regions will not produce solar flares. Some will produce multiple of different class. X-ray flares are very less as compared to M or C class flares. So the data imbalance is huge, and that's a bottleneck in data-driven learning through ML-based methods. Not sure about the physics-based and MST simulations, but I think they're too expensive for operational forecasting purpose. But yeah.
And also, like since you mentioned about the smaller flares, because till goes we weren't able to identify say A class flares, which Chandrayaan's XSM showed that there are abundant of A class flares, which it's all about sensitivity. So we don't have that much data to understand like the at what scales or the smaller reconnections are happening and causing the flares. Okay,
So,
someone SKS has a question.
can I add something to it?
Yes, Priyansh.
So, one of the bottlenecks I think is that still most of the flare problems or the flare prediction solutions that people are presenting are being treated as black box. So, they give data as the input, say sharp parameters or images, and they simply ask, will it produce a flare or not? There is no connection between the question we are asking and the physics we have discovered so far. So that if we constrain the problem better with the physical understanding that we have of the flare right now, that might increase the prediction or might improve the results as well. Otherwise, we'll just keep on waiting for more data to get a better statistics, but that might not be a very efficient solution as well.
I think
Yeah,
in
I
this
can just
front.
add a few
Oh
things
yeah,
to
yeah, go
what
ahead.
Priyansh has just. Yeah, just we are using the sharp parameters for most of the to drive the models, but from my initial studies during the PhD, I have seen the same sharp parameter, what you are getting as a mean from whole active region, that varies a lot, like the temporal variation. If you look at the spatial at different location of the active region, and particularly when it is associated with the flaring location, so those evolution are completely different. And if you take the average thing, that actually dilutes on
Yeah,
that, it
right.
takes average out. So these things also needs to be considered. Yeah.
Nice point.
Yeah, adding to that, what Priyansh mentioned, so maybe physics informed neural network or pins, as we say, that can be a next thing to try instead of treating everything as black box. So whatever we know about flares, and Pratik is an expert in ML, maybe he can.
But this is a kind of classification problem, right? So how will you put physics in it? Means we have just a 2D map and we have to say yes or no with some intensity. Um, so yeah, I don't know how to put physics in it.
Like
Maybe some people might have tried. Yeah.
like Randeep was telling na ki that the sharp parameters is just average in the box, but it can have further details. So those details can be absorbed to train better
Yeah,
models.
but you also give the full patch, active reason patch, and in addition to that, you give those sharp parameters. So you can remove it as well, or you can also add. It has been seen that if you add player history of the active region, means that active region whether that has produced a flare or not in the past, that also enhances some accuracy. And if you add UV images, that can also enhance accuracy. But some studies says that it confuses the model. So right now it's khichdi. It's totally confusing what works, what doesn't.
Yeah, so that's still an open question. So we can take one last question before closing the discussion. So does the strength of solar flares varies as solar cycle progresses? Who would like to take it?
I can, if I may. So,
Yeah, go ahead.
yeah, during the solar maximum, you'll have, so short answer, yes. During the minima, you have less active regions. Eventually, you have less flares. And as the cycle progresses towards the maxima, you have more complex active regions, bigger active regions, more flux content, more pool for release of energy. So you have higher chances of having stronger flares. So if you simply make a plot with the number of flares over the years, you'll see that it follows a solar cycle trend as well. So yeah, it follows a one-to-one relation with it.
Yeah, I think if you refer to Gopal Swami's some of the statistical papers, he has also got some solar cycle variation for at least 2 solar cycles. Yeah, okay, so we are a little bit of overtime in spite of having 2 less talks. That was it shows that we had a very nice, healthy discussion. I know people may have further questions, but it's about time, and I hand it over to the organizers if they have announcements, and then we can proceed to break as required.
Yeah, no announcement as such. We'll have same setup as yesterday. Flash talk and then panel discussion and then invited talk. And right now, maybe we can have a screenshot so that we can have this as a memory, post on a social media. Ketki, can we take a screenshot? Maybe remove them from spotlight and
Okay, I hope everyone's camera, whoever wants to on, is already on. Okay, please, guys. Another one. Thank you so much.
great. Thank you, everyone. Thank you for joining.
Thank you.
Who is recording?